No, for now you can. I don't know. Like, let me try.
Hi.
Turn
Hello,
this on,
hello.
you have to
Test, test.
Hold the button down for like.
And then you can start talking. I think that's good, and it's recorded. You don't have to hold anything.
Yeah, I don't
think that's
we
good.
do like celebrity style talk.
No, like where you.
Yeah.
We came up.
Huh?
We came up with this.
All right, let's get started. Hello, everyone. It's my great pleasure to welcome you to the Julia for High Performance Computing mini symposium today. My name is Carsten Bauer. This is Samuel Omlin. He's from CSCS. I'm from the Paderborn Center for Parallel Computing in Germany. And we are the organizers of today's mini symposium. And we've prepared a few intro slides just to get everything started, talk a little bit about what has happened in the past year in the Julia HPC space. And then we have compiled a hopefully nice and interesting program, lots of speakers from different institutes, different countries, and I'll get into that in a second. So, as I said, what has happened in the past year? I've just put a few things here. Last year at JuliaCon 22, we had in a virtual format the very first Julia for HPC mini symposium. Perhaps some of you have watched it online. So this is the first in-person one, the second overall. We are looking forward to making this a tradition. Hopefully that will happen with your contributions. Right then, otherwise, at Supercomputing in Dallas last year, we had the very first Julia for HPC Birds of Feather session. Just a second ago, when we took pictures, I thought I should have put a picture of that BOF session here. I forgot about it because I can tell you it was packed. It was packed, and in particular by non-Julia users, which is good, right? Because it's an outreach event for us. So you just have to take my word for it for now. But that was a great success. And then at SciM earlier this year in Amsterdam, right, there was a mini symposium for research software engineering with Julia. Another great event that I didn't attend, though. You were there, I think. And then in PASC, just a couple of weeks ago, that's a conference for more on the application side, computational scientists in Switzerland, in Davos. We also had in fact, a one-day Julia for HPC mini symposium there, 2 blocks in the morning, in the afternoon. So what I'm trying to say is lots of things are happening. We are present at conferences. Obviously, I only put the conference part here. There have been lots of workshops and tutorials going on at ETH, at HLS in Stuttgart, at the eScience Center in the Netherlands, right? Lots of other places. Part of ECP, PRAISE, lots of these national HPC funding programs. And obviously, if you have conducted an event that's not on the list, reach out to me because we want to connect and build a community. Feel free to reach out and join us. What else has happened? There was a community paper put out on the archive by a bunch of the folks, some of which will also speak here today, including myself and Sam, but also Valentin and some of the faces that are omnipresent, I guess, in the Julia HPC world. Feel free to check it out. Again, it was a cross-continental collaboration, lots of people from different places. Right. That brings me to the schedule for today. The schedule is composed of 3 parts. That's also how it's presented in pre-talks, I think, as 3 separate blocks. The first block is what we dubbed scaling applications. So this will be from application scientists, talks about how they use Julia for their scientific explorations. So Ludovic will give a talk, Dominik, Michael Schlottke-Larkemper, and Henrik Ranoka. The third talk will be virtual, unfortunately, the only virtual talk today. The second part then will be from the HPC Center side of things a little bit. So if William Godoy from Oak Ridge and Moses Giordano from UCL, then myself will give a little talk about tooling. And then we will have the big lunch break, including the photo. I'll remind everyone of the photo. So Ranjan said 12:30 sharp, and I'm trying to get you all there. So we'll remind you of that. And then after the lunch break, we will have the third part on ecosystem developments. So Tim from Julia Computing will talk a little bit about OneAPI, Julian about Dagger developments, and Johannes a little bit about distributed. So I hope that's an interesting schedule for the next, it's not the next 3 hours because there's a lunch break, but overall 3 hours. There will always be the option to ask some questions after the talks. And then at the end of every session, we have a few minutes for overall talks, overall questions. But there will be plenty of opportunities to talk to us, obviously, also outside that mini symposium. Oh, whatever happened there? Why did it jump in front of my presentation? Whatever. So I'm in a Zoom meeting for Michael and Hendrik. They will show up in a second. All right, but speaking of asking questions and getting in touch, tomorrow there will be a Birds of Feather session for Julia and HPC at 3 p.m. in this building in room 144. And obviously, it would be great to have you there because that's a more discussive format where you can, complain or ask questions or tell us what great things you do with Julia and HPC.
Emphasis on the complaint.
Emphasis on the complaint. Valentin will take those on specifically. All right. Yeah. No. Obviously, it would be great to have you there and hear feedback from the community, and we'll look forward to that. Finally, get in touch. I have to mention the regular channels where you can reach out to us and participate, become a member of the Julia HPC community. The obvious choice is the Slack channel, #HPC on the Julia Slack. There's also a monthly call organized, which I think this is still correct, the fourth Tuesday of the month. It's mostly most of the time the last Tuesday of the month, but technically not always. So that's why I write it like this. If that's too confusing, just go to the community calendar of julialang.org, and there you will find the correct date and time and Zoom link and everything. Yeah, looking forward to seeing you there as well. And now I think we have a few minutes left before the first talk. And I'll hand over to Sam, which will talk about the survey.
Yeah, we have 3 minutes. Every year we also want to do a little survey to see how the Julia community develops, what are the interests, what are the focuses, what kind of things people want to do, etc. And so you find it here. How do we get there?
We'll bring the QR code and the link back in a second, and we'll also show it multiple times today. I'll just go away to quickly show it.
Yeah, so this is the survey. And so you will have questions like, do you use HPC systems? Do you use small scale or large scale applications, etc., etc. So if you would fill that out, that would really be appreciated, such that we can see as a community where we are going to.
Maybe let's put back there's the code, and yeah, we'll give you right now already 2 minutes. Again, you can fill this out later today, tomorrow. We'll show it in the BOF as well. Obviously, only fill it out once. That would be nice. And in 2 minutes, we will have our first speaker, which will be Ludovic. All right.
Please.
Sure.
Is the BOF tomorrow specifically HPC focused, or can I come and complain about GPUs?
I'll guess we take on GPU complaints as well. Yeah. Yeah, absolutely.
Oh, absolutely. But you can take a little bit.
It's everyone knows. That's a fair assumption.
All right, while he's setting up, our first speaker, Ludovic Ress, he's a researcher at the glaciology lab at ETH Zurich, and he's going to speak about his GPU work with collaborators. Take it away.
Oh, super. Well, thanks, Karsten, for the introduction, and well, welcome everyone to that mini symposium. And I'm happy to be to open this exciting session. Yeah. So what I want to kind of share and discuss a bit today is somehow scalability and kind of HPC readiness, let's call it like that, on Julia's GPU stack, targeting supercomputers, and in particular, like the kind of latest generation of supercomputers that also made it to the exascale, which are powered by AMD devices, so AMD GPUs. And yeah, I hope that, with what I'm gonna cover, I kind of feel that's really important, because that's also where Julia and Julia for HPC, I guess, can stand out compared to maybe other approaches in terms of, I'd call it portability in many ways, but hardware portability, but also kind of development portability, like two-language barrier that can be overcome and that one can basically rapidly prototype and port kind of research code, not community software, like research code targeting specific problems, in a pretty efficient way to deploy on supercomputers, and not on only one type of architecture, but also on different type of architectures, which is like, NVIDIA, AMD, soon Intel, and who knows what comes later, maybe IPUs like from GraphCore, and so on. And I guess that's really, I really kind of see that's one of the key and the power of Julia there. So before kind of diving some technicality, just quickly what do we do? So I'm kind of working for now in the glaciology lab at ETH Zurich, and where we're working on a piece of software that's called Fast Ice, and guess what? It's to model ice flow. And now we just got kind of extreme scale European grant to try to simulate and understand. So what you see here is the ice flow speed over Greenland. Where it's red, it doesn't move. Where it's red, it doesn't move, and where it's kind of purple, it moves like at meters to kilometers per day. And those are called like those things here. They're called ice streams, and it's basically that's a big problem. So if we kind of don't account for the ice melting because of the sun, so kind of the ice flowing out of the ice sheet, it's kind of 99% flows out through these couple of streams. And we see them, but we still don't understand why they appear here and here, and why there are maybe only 10 of them, and why not others, etc. So for this, one needs some advanced modeling, and we were granted about 5 million GPU hours on Lumi supercomputers, so like the little replica of Frontier, that kind of still makes it number 3 in the top 500. And one important part is to run forward models, but ideally we also want to make UQ and inversions, etc. So yeah, why we do it is kind of this, we zoom in one of these streams. Basically, you see that where it's here, where it's red, it moves fast, so it's kind of viscous fingering, and where it's blue, it doesn't move. And then you have this shear margin, like this region where you have extreme shearing, and kind of you can imagine if you shear thing fast and it heats up, it melts further, etc. So they're pretty much nonlinear interaction that one would need to resolve if one solve this, try to get a numerical model to resolve this. And also not only at the streams, but at the bedrock. So that's the other picture. So basically, we want to understand why kind of, or we believe that kind of the roughness of the bedrock would further kind of lead to localization. And then one need to resolve this in 3D to understand where one gets localization of flow and where not. So yeah, how we do it, we kind of developing full Stokes models, so kind of no rocket science, but kind of let's call it classical HPC, but with kind of new tools. And yeah, we kind of still develop some, try to come up with kind of iterative solvers that can leverage parallelism of GPUs and multi-GPUs. And yeah, we also can account for these different boundaries. So there are some preliminary results, for example. So here it's just a synthetic where we're testing something. So that's kind of a valley with a bumpy bed, and the arrows are the ice flow velocity. And if I kind of play that thing, we'll see that kind of if there is forcing over time, it would speed up, and then it would start to create at the very end some lenses, and this is contours or, well, sorry, these lenses that come, this contour where basically there is kind of this shear heating going on, so where we would get like kind of melting of the ice and rapid like runaway, and that's kind of shown here in red. So basically, that's those kind of things that we want to resolve at kind of physically 10-meter scale over entire Greenland, and that's what we need a supercomputer. So how we do it? So we kind of took the choice to give it a try and like proposed and got funding for that to use Julia and AMD GPUs on Lumi. So I guess we're the only project doing that. Yeah, so the cool thing, as I said about Julia, it's kind of we can come up with tools to try to support this variety of backends, maybe threads, multi-threading, like just threaded threads, for example, but then also CUDA, and now AMD GPU, where I was a bit more involved, and there also I have to kind of, that was work we started also with Julian Samru, and now Anton Smirnov from AMD proper, who helps and kind of takes a bit over the AMD GPU stack, and kind of we managed to get that package that was just getting started somehow closer to the standard and like kind of getting more and more towards what CUDA.jl sets up, with NVIDIA being around for many years. And where Julia is really important there is one can really try to have, or how we try to come up with a thing is come up with a single code base that can leverage all the different backends such that, well, we can just upon changing a single parameter, just make that the entire stack would kind of, yeah, run and become basically deployed on a different architecture. And what we also want, so we want to be able to leverage like this portability that Julia offers to have like prototyping. I mean, I'm commuting to work, so I usually work in the train, try to run my thing on my little computer in Flow32 on the M chip, and then while I want to kind of try it in 3D, etc., I just kind of connect to the supercomputer, and then I scale it up to thousands of GPU, and kind of that's the thing that that simplifies my life as a researcher, and so we'll try to make that happen. And yeah, on the sensitivity analysis part, so for those huge 3D simulation, you cannot afford like MCMC and other things because there's just too much dimension. So there we kind of now try to leverage AD and gradient-based optimization, and well, that was the topic of the workshop that we gave on Tuesday. So how to make this scalable, parallel, etc. So yeah, just a simple, so kind of we developed some tooling around the backend abstraction, and here I just highlighted, so that's kind of an explicit diffusion code here, written using Parallel Stencil, one of the packages we develop. So it supports stencil, like there's a way to write stencil operation in a math clause formulation, supports our backend. So here, when we init Parallel Stencil, we can pass the precision, the number of dimension, and the backend, so threads, CUDA, AMD GPU, metal to come at some point. And yeah, recently added also AD support. And so, well, that little code here would run like on all these different kind of backends, and it's under the hood, it would do some performance optimization to leverage shared memory, register queuing, and all these things that's done for kind of under the hood, and well, just make the code to run as optimal as possible on, well, different type of hardware. So regarding AMD GPU.jl specifically, so we kind of start the project, and we have access on Lumina for not so long to do some proper scaling, but that's the status. So the AMD stack in general is not as mature as, for example, the CUDA stack, but AMD, or like Julia, does pretty well in that thing, because basically we get with AMD GPU for memcopy or diffusion kernels, we got the same results as heap C++ code. So, well, we are there, and I mean that's really that was a really great achievement, especially that we kind of pretty much refactored AMD GPU.jl like a couple of months ago. Then, well, that was on a single device or single GPU, but now we want to scale up, so we want not to use one GPU, but thousands of GPUs. We need to use something like, well, we use MPI here, and there we also develop something that's called implicit global grid to, well, make the distributed domain decomposition. And so if I take the same code as before, I now use implicit global grid, and I only need to call 3 functions to make that happen. So I need to initialize my global grid in the main part of the code. Then I can make an update halo, so exchange the internal boundaries of the array H that I need to, that basically my physics don't know that they're cut into pieces, and at the end just tear down the MPI and the global, the implicit global grid. And on top of that, we introduce something so we can even hide computation behind communication. So it would make these fancy things such that, well, basically you can scale up to, well, you can hide the latency of the communication if you have like some networking thing and like the standard issue when you scale up to many, many processors. And with this approach, we get like super good parallel efficiencies. So that's kind of increasing. So that was on NVIDIA GPUs, and that's on AMD GPUs. So up to 2,500 GPUs from running a local problem on one GPU and then going for a 500 times bigger problem on 500 GPUs. We only lose like 3% of efficiency with the whole machinery, leveraging a good part of the machine. And that's achieved like in the timeline of the profiler. For those who are familiar with that, well, basically these little dots are the kind of MPI communication and all what's related to exchanging the internal boundary, and then we can like hide them behind computation of actual physics that we would anyway to have to perform. And the last little super cool bit, and I mean that's really where I guess at least since a couple of months now, I really sell this as like, that's really where Julia stands out in general for scientific computing as we do it, is that the stack is differentiable. And that's really a big thing because other languages, like it's really, well, it's not there, or it's a pain, or it's expensive because you have to buy licenses for old software. And so basically now, if we want to get the gradients of those kernels, we just kind of pass this, so the gradient argument in the kernel call, and I'll initialize some shadows, and then say that, well, now we'll store or accumulate the derivatives, basically, of this term with respect to other terms in those bar terms. And this can be, like, again, if you followed or watched back the workshop from Tuesday, this can then be readily used to combine to get gradient and make gradient descent and optimize for a parameter in those things. And really the cool thing, so here I also kind of kudos to like Enzyme and people who are working on that and also who are very helpful. So the performance is actually pretty good. So Enzyme runs on GPU, it would analyze the GPU code and create for you a new GPU kernel that would again run on the GPU, and all this is done automatically. And the costs for now, at least, is only kind of, so the effective memory throughput, so that's kind of the performance we get running the forward pass of the kernel, and then the enzyme-generated kernel that accumulates the gradients and derivatives runs at 50% of the forward pass, but which is great. Can be better, but it's already super. And why it doesn't matter so much is that the adjoint solve is linear, so we need much less iteration, so much less call to that function, and at the end it's kind of negligible compared to the forward solve, which is really a big thing. So yeah, well, with this I'm done, and well, I thank you for your attention.
Thank you, Ludovic. We have time for a few questions right now. Go first. Microphone will be there in a second.
Just a quick problem. What are you doing on slide 10? What's your problem that you parallelized?
Oh, here it's the thermomechanical 3D Stokes problem. So kind of incompressible Stokes with like nonlinear viscosity that's coupled to temperature source term, like shear heating and nonlinear viscosity in the Stokes. So 3D Stokes, double two-way coupled to temperature.
Hello.
Hey.
Nice to see you again. Can I ask you a question about absorbing boundary conditions? I saw an issue I think it was parallel stencil. I don't remember if it was parallel stencil or implicit growth or grid.
Parallel stencil.
But it was talking about using PML boundary conditions on wave equation propagations. Do you guys have any update on that?
Yeah, so somehow the person that opened that issue didn't...
Right?
Sorry?
Disappear, right?
Well, yeah, it's kind of, apparently it was ready, but I never get the pull request. And now I have there's a student at ETH who made like some brain MRI using parallel stencil in the wave physics group, and he has it, and I guess we'll kind of have his development. So it's there, or it soon be there. Super, thanks.
All right, we have to move on. Further questions can be posed later to Ludovic, who will be around. And the next speaker is Dominic Kiza. He's a postdoc at the Flatiron Institute in New York, and he's going to speak about his multi-threaded physics, condensed matter physics in Julia. Take it away.
Great. Okay. Thank you, Carsten, for the kind introduction. Today I'm going to be speaking about vertex calculations in condensed matter physics using Julia. So when you hear vertex, you might be thinking of something like this. So some geometric body, or if you will, some connected graph. And then the vertices are the corners of the tetrahedra, or the points where multiple edges in this graph intersect. So the objects that we will talk about today, they look a little different. They mostly look like this. So in general, when I say an endpoint vertex in the context of condensed matter physics, I mean a rank n tensor, where the different indices x, they capture all the physically relevant degrees of freedoms, which are here denoted by alpha, beta, gamma, and so on. So why would we be interested in calculating such an object? So to explain that, I will briefly dive into strongly correlated electron systems, which are one of the current frontiers of condensed matter physics. So the difficulty when studying these systems is that they intrinsically require you to take a many-body perspective. So you cannot just treat the electrons as individual particles, but you really have to consider their collective interplay. And one of the simplest, somewhat realistic models that we have to describe them is the so-called Hubbard model, which basically consists of three terms in this quantum mechanical formulation. The blue term basically describes the movement of the electrons on the atomic lattice, as shown in this little sketch below. The red term is just the repulsion of two electrons of opposite spin when they sit on the same side. And then this black term basically controls the density of electrons that you put in your system. And although this Hamiltonian only has three parameters, T, U, and mu, you already find a variety of different correlated phases in them, including magnets, superconductors, and even more. So what we want to do in a theoretical computation now is we want to compute correlation functions to characterize these different phases. One example is shown below. This is a dynamical susceptibility, which basically describes the response of your system to an infinitesimal external perturbation, such as a very small magnetic field. And as you can see in this expression, in this diagrammatic formulation, the thing that we need to compute in order to be able to compute such an observable is a vertex function. Okay, let's take a step back and look at this object again, and let's do some naive scaling. So as I said, these x, they correspond to the multi-indices which capture the physically relevant degrees of freedom, and these might include the lattice index, spin, frequency, or more. So for this 4-point function, you could say, okay, that's great. That means that in the dimension of the different physical degrees of freedom, we will only scale polynomially. But you already see it's to the 4th power, so the computational memory resources that we need to resolve that, they will actually grow quite rapidly. And if you go to higher order vertex functions, so you basically increase, the exponent, to higher rank vertices, you see that your scaling gets exponential. So in most applications, we actually restrict it to computing these 4-point functions and not even higher order vertices. So before I show you some improved scaling, including the symmetries of a Hamiltonian, I first want to talk quickly about a method which we use to compute these functions, which is called functional RG. So the details of that method are not important. The interesting part of this is that the vertex function is computed by solving a system of coupled ordinary differential equations, as shown here on the left. The special flavor of the FRG that we will use for the sake of this talk is the so-called pseudo-Fermion FRG, which is a special FRG method to treat quantum spin systems, for which there also exists a registered Julia package. So now what you need to do to integrate your differential equations is you will evaluate the right-hand side. And in order to do that, you need to compute these contractions that you see between these vertex functions, which means that you will need to sum over all the discrete degrees of freedoms that you have and integrate over all the continuous ones. At 0 temperature or in real frequencies, for example, you would have to integrate, with frequency, sum of the spin, the lattice index, and whatever. And these integrations, they actually have to be carried out adaptively. If you don't do that, you see that you get these gross numerical artifacts for the asymptotics of your observables. And in addition, even for just moderately sized systems, the number of differential equations that we have to solve actually ranges between a few 10 to a few 100 millions. So we actually need quite some efficient code to do that. The good news is that all of the different components of your tensor can be computed independently. So the evaluation of the right-hand side and all of these contractions can actually be massively parallelized. The bad news is that due to the adaptive integration and due to different complexity of the diagrams on the right-hand side, the workload that we get will actually be highly asymmetric. So far we only got the code to scale very nicely in shared memory, where we actually rely heavily on dynamic load balancing with Julia's threads.add-spawn, and we also need to vectorize where possible to actually also make use of advanced vector instructions when switching to the cluster, and this we do by using the loop vectorization.jl package. So this is a quick example of how this calculation then actually looks like. I don't know if you can read this, but just in the overall structure, well, you have these different blocks that you see, these 4 blocks. These correspond to different complexity classes of the diagrams, and these are scheduled as individual tasks. So one thing that you can also see is that so far we were actually using thread local storage, which is now actually discouraged because it's unstable, because the threads might migrate between tasks. So actually, going to future versions, we will have to do some rewriting of that code to actually make it robust. Okay, so now let's come back to the scaling part, and let's actually talk about what we do to simplify the problem. So you can drastically simplify the whole calculation if you include the symmetries of your Hamiltonian. For example, remember that for this 4-point function, we would actually scale to the 4th power in the number of frequencies. But actually, if you include, for example, energy conservation, we actually only scale to the 3rd power, which is also nicely reproduced if we test the scaling with our code. So what's even more important is the use of lattice symmetry. So what I show here in the lower left is actually the number of lattice sides as a function of the bond distance for different 3-dimensional lattices. And you can see that using symmetries, the number of sides that you actually need to include is reduced by almost 2 orders of magnitude. And since, after all is said and done, the code scales quadratically in the number of sides, this is a massive improvement and actually makes the whole calculation feasible. So to end this talk, I want to quickly, show some results for our scaling analysis on different shared memory platforms. So here we have 4 different CPUs, 2 Intel, 2 AMD CPUs, installed on different high-performance computing facilities in Germany. And as you can see, the scaling that we get is almost ideal on all the CPUs except maybe for the Xeon Platinum. Actually there, we were a little puzzled what's going on. So you see that the scaling falls off slightly after around 16 threads. But actually, when we benchmarked the single core performance on this CPU, we actually found that our code in single core runs is actually faster on this CPU than on the others. So we actually think that this might just be because the benchmark problem that we use to do the scaling analysis might be a little bit too trivial for the CPU to treat beyond 16 threads because we don't have the full throughput on all the cores. But that might require some future investigations. Okay, so with that, I'm at the end of my talk. I thank you for your attention, and I'm looking forward to your questions.
All right. I'll take this one. I'll take this one. This works. All right, we have time for a couple of questions.
Yeah.
Go first. Yep, sure.
That last scaling plot you showed?
Yes.
Was the workload floating point bound or memory bandwidth bound?
Well, Yeah, I think it's actually memory bound more or less, yeah. So actually the operations that we're doing, they are not so heavy, but what I didn't say is that when you basically try to call this vertex function in the integration, you will have to evaluate it at points which are not necessarily in the grid, which you use to discretize, right? So you need to do some interpolations, and you need to like access this thing, over and over and over again. So I think it's more like, yeah, it's a more of a bandwidth problem than I think the floating point operations.
Do you do anything for NUMA?
Yeah, we tried looking into that. So we started playing around with this and try to for example allocate different parts of the array on different NUMA domains, so we can actually get better performance. And this gave us some improvement, but it was not as huge as we would have hoped in the end. But a few percent is still a few percent if you have to run a calculation for several days. So.
Hello, thank you. About the last slide before this one, did you perhaps test like using 2 CPUs on the same motherboard, like using in the same node?
Come again?
Did you test like using these same processors but 2 on the same motherboard in the same node?
No.
This
so far,
scaling
no.
is only for. Is this scaling there only for 1 CPU or for 2 CPUs on the same node?
No, this is always using the full CPU stack of one node.
Okay,
Yeah.
so it might be that the node has 2 CPUs.
It might, yeah. So that might also factor into the scaling of
No,
yeah.
I'm asking because perhaps these Intel Xeon Platinum
Yeah.
communication between the 2 nodes might be just bad, right? But in 2 nodes, no, the 2 CPUs in the same node.
I can just tell because I know that bottom right system very well. So that's both sockets, both CPUs.
Oh, I see.
So
Okay, so-
and there we don't see the drop. So
Yeah.
just saying.
But is this motherboard? Because maybe the motherboard is different.
You can take it offline.
Might be. So we'll probably have to test it further. So.
Like, was hyper-threading enabled in the?
Sorry?
Hyper-threading, was it enabled in these
It was enabled in this run. Yeah, it was.
All right. We could do one more, and then we would have to move on. Is there one more question?
Great.
If not, let's thank the speaker again. Where's the cable? There. All right. All right, the next talk will be a virtual talk. Unfortunately, Michael and Hendrik couldn't join us here today. So Michael is an interim professor at RWTH Aachen, and Hendrik is a assistant professor at the University of Hamburg. The talk will be given, was pre-recorded by Michael, and afterwards I will hopefully have them, at least one of them, in a Zoom room. I saw one already joined. Let's hope that the technical thing will work out. So I'll play the video now, and then we can hopefully ask them questions after the fact. Let me try this.
Hey everyone, my name is Michael Schlottke-Larkemper, and together with Hendrik Ranacher, we will be sharing some of our experience with scaling TrixieJL to more than 10,000 cores using MPI. Before we get started, I would like to acknowledge the great TrixieJL community. There are a number of people here on that list without whose contributions the results that we're presenting here would not have been possible. So first of all, what is TrixieJL? Trixie is an adaptive high-order simulation framework for conservation loss, obviously written in the Julia programming language. We have 3 major design goals. First of all, this should be an extensible code useful for our own research. It should be usable enough that we can also do projects together with students, and of course, performance is a major issue. Trixie is integrated within the Julia ecosphere, and we make use of a number of packages, for example, ordinary diffq for time integration, polyester for multithreading, and of course MPI-GL for distributed parallelism. So what are the kind of simulations we're running with TrixieGL? What kind of numerical methods can you use here? This is a simulation of a supersonic flow coming from the left. There's a little obstacle here with this little cylinder here. You can see there are curved walls, so we have a high order in space and time discontinuous JuliaCon method. And we use adaptive mesh refinement, as you can see in the lower left corner here. So the mesh adaptively refines where something interesting is going on in the solution. Another example of what the kind of simulations we're looking at is the shallow water equations. This is a simulation of a flooding event in the seaside town of Seaside in Oregon. We use real world data here to model the geography here, and we can predict how the water in case of a flooding event would distribute and flow back. So these are just two examples of the kind of simulations we can do with the TrixieGL. But today we want to talk about parallel performance. And before we talk about parallel performance, we have to look at serial performance, of course. So for this, this actually results from a paper that we already published 2 years ago. This is a 3D compressible Euler simulation setup for the envisaged Taylor-Green vortex. We use a curvilinear mesh with entropy conservative fluxes. So this is only relevant if you care about discontinuous JuliaCon methods. And to evaluate the performance, we compared it against a Fortran-based simulation code that is already very mature and optimized. It's called Fluxo. And when we look at the result, we see here a number of curves. In this plot, lower is better or lower is faster. And we see the top curve here, that's Fluxo. For a number of polynomial degrees, we're looking at the time per right-hand side and degree of freedom. So less time is better. The Trixie baseline curve is in green, so this is basically where we started off. And then we, in this paper, we put in a lot of effort into further optimizing these methods, and then we ended up with this blue curve, which was even better than the original implementation. So the key takeaway here is that TrixieGL is a fast serial solver, and that, as usual, we do not claim that Julia is somehow faster than Fortran, but that the actual performance really is only dependent on how much time you spend optimizing your code. So before we started with the parallel scaling experiment, we had one thing in mind, and that is the memory usage in Julia. So we've noticed that the Julia memory usage has been increasing since Julia 1.6. With each new Julia release, the memory usage goes up. And this is a plot for the maximum residence set size after certain operations done in Julia and for different versions of Julia. So we're looking at 1.7, 1.8, 1.9, and a pre-release version of 1.10. Disclaimer, with the final 1.10, the numbers will be different and probably a little bit better, but this was when we did this. These were the results.
I don't
know how good my connection is, so we'll see.
Yeah, sure. At least I should be able to stay in here.
Okay, it's great that you made it.
Hey guys, do you hear me? We are already watching your video, so it would be good if you won't speak for the next couple of minutes. Sorry for that. Talk to you in a second, but great to see you and great that you're here.
Sorry.
And as we can see, with each new release, the memory usage grew. So this is the baseline usage. Then after using Trixie, we're already with Julia 1.9, for example, at roughly 800 megabytes of memory usage. Using ordinary diffq pushes this to 1200 megabytes, and then running a simple simulation to almost 1.5 gigabytes. So while this is okay, sort of okay-ish if you have a hybrid code that uses MPI and threads or GPUs, that's problematic for MPI-only parallel codes. And this is actually what we wanted to do in our numeric experiment. So for our parallel scaling, we used the Eureka supercomputer at Jülich Supercomputing Center. And this has a very nice property that on each compute node, which consists of 128 cores, we have per node, we have also 4 gigabytes of main memory per core. So even when you look at the memory, the high memory usage of Julia, there's at least roughly 2 to 2.5 gigabytes of memory available for the application itself. So basically excluding the Julia memory usage. All right. So this is the first parallel scaling result we got. This is a strong scaling experiment on Eureka with Julia 1.8. Strong scaling means we have a fixed problem. We start with a low number of ranks. So we have 128 ranks on one node, so one rank per one MPI rank per core. And then we take the same problem size and just distribute it over more and more nodes and more ranks, and see how the performance works out. So this has roughly 17 million degrees of freedom. And as we can see, we have a good scalability to 16,000 to roughly 16,000 ranks. In this case, higher is better. Here we're looking at the number of degree of freedom updates per second. And as we also can see that Trixie has a near linear scaling on this scale, and a similar result is for the Fluxo code. We can also see that Trixie is slightly faster than Fluxo, but this is not a surprise. We already saw that it is slightly faster in the serial case. The key takeaway here, however, is that again, we have a comparable performance as the Fortran-based Fluxo code, and especially in the CFD world, Fortran is still the major workhorse language for high-performance computing. So we cannot expect to be better than Fortran, but if we are as good as Fortran, this is a very, very good result for us. So, of course, we also wanted to go to higher core counts than 16,000. However, we investigated and looked a little bit at the startup latency. As you all know, Julia is a just-in-time compiled language, so you have some sort of startup latency. And we looked at things like compilation time and code loading time. And up to 2,000 ranks, everything actually was quite nice. So you see different curves here. For example, orange curve is compilation time. And for example, the purple curve is using ordinary diffq. That stayed fairly constant. But with more than 2,000 ranks, the purple curve started to grow quite fast. So with 16,000 MPI ranks, we're already at more than 10 minutes of waiting time just for executing the command using ordinary diffq. So obviously parallel becomes a bottleneck. And if we want to go to higher core counts, this is not going to fly anymore. I mean, we're just burning CPU hours doing I/O, or basically waiting for I/O. So we had to come up with a solution. And the idea was to create the Julia depot in the RAM drive. So basically trigger precompilation on your compute node, on your login node, sorry, then tar the depot, and then when you do a parallel job, you just take the entire depot, upload it into your node local RAM drive, and then just be happy about it. And this actually worked quite nicely. When we now look at the purple curve, we can see the dashed curve is now with the RAM drive. The continuous line is the original curve that you just saw before. So while the original curve, the loading time goes up sharply after 2,000 ranks, we now have a very nice, flat, constant loading time when we do using ordinary diffq. So problem solved. And now we were able to do a scaling to a much higher node count. Actually, we used the same setup as before. We just increased the initial resolution. We're still using the invisible Taylor green vortex, but now with 134 million degrees of freedom. And we can see, again, we have good scalability from 128 cores to over 60,000 MPI ranks, which is the full Eureka machine. So we were not able to scale this any higher on this machine. Still, it's a very nice 400x speed up. And at the high core count, we actually have only 34 DG elements left per MPI rank. So what are the conclusions? First of all, I introduced Trixie as an extensible, usable, and fast framework for numerical simulations. We were able to show that we can get good parallel scalability to more than 50,000 cores. And the key takeaway message here is that, yes, Julia is capable of doing HPC computations, also in traditional HPC applications like computational fluid dynamics. the serial and parallel performance is similar to Fortran, so there's no reason to not use Julia for these kind of workloads. Although there is a small caveat, there are still some challenges, for example, the startup latency, but there are ways to work around that. In the future, we're of course trying to push this scalability to a little bit further to go to more than 100,000 cores. We also want to look specifically at other ways how we can reduce the memory usage to also do this on other machines, and we want to look at GPU computing. So thank you very much for your attention. I'm happy to we're happy to answer questions, and if you have some questions later, you can always reach out to us via our GitHub webpage. Thank you very much.
All right, guys. Now would be the question and answer session if you are there. Let me turn off the virtual background. Whoops, no, where did it go? All right. Decided to reconnect. What's going on? All right, let me try to reconnect entirely. I am, right? Yeah. Edelman. It was working at the wrong part of the talk. No, that's not an issue. I mean, ironically, it always happens.
Works the second time.
It always works the second time, yeah. Right. So let me. Let's see if they are still there. Looks like it won't work, unfortunately. I mean, it was working as you... Sorry? Yeah, I can try another Wi-Fi. Oh, there we are. There we are. Hey, guys, can you hear me? Michael, Hendrik, can you hear me? They are muted, but I can't see you guys. Maybe...
You can ask them to unmute.
Maybe try something.
I mean the... Yeah, let me try the chat. We have a few minutes, so the... Oh, yeah, now I heard something. I think the Wi-Fi connection is bad. I'll be back in a second. I'll try a different Wi-Fi here. Bear with me, guys. Oh, no, leave the meeting, yeah. Assign and leave. I should have followed the advice on the blackboard downstairs, obviously. Right? Let's try this again.
We can also try turning off video if that helps.
I think it works now, guys. Sorry, I think that was a technical issue on my end. Edelman is only working in parts of this building, and unfortunately not that room, apparently. So let me try to turn this around so that you can see some of the audience. Just give me a second.
Okay, I think I'll go ahead and ask my question. That's fantastic work, by the way. Very, very impressive to be able to do a fluids HPC in Julia like that, comparably with Fortran. But now, how about the software end of it? What's the how is the Julia as an improvement to Fluxo in terms of development time, comprehensibility of code, flexibility? What are the pros?
I'm not sure if you understood the question, so let me repeat it. The question sort of is, what is the improvement of Trixie compared to Fluxo when it comes to development time, comprehensibility of the code, so the software aspects?
Maybe I can take this question. Thank you for repeating this. And first of all, I'm really sorry that we were not able to make it in person to this conference. So in terms of usability and in terms of features, I think these are two pairs of shoes. However, one thing that we noticed from early on is that when we started developing Trixie, it was extremely easy to get students interested in working on that code, and it was also it was very easy to get other researchers working on this code, because it was just so much easier using the modular approach that Julia allows one to use for such kind of simulation softwares, that other people could, just focus on a particular bit of the code and then try to change it, put in some new physics, put in some new numerics, and then see if it works. Whereas with the old code, which is still a very capable and state-of-the-art research code, it was much harder to get students to the point where they could contribute meaningfully to it. Does that answer the question?
Yes, it does. Thank you.
How about line count or something?
Just one follow-up question. What about line count? Can you comment on that?
I think line count is hard to compare because we use different paradigms for Trixie than we used for Fluxo. So, for example, Fluxo is inherently a 3D code, whereas in Trixie we also support 2D and 1D computations. So that, of course, changes a little bit. Also, I would say that because in Trixie, from the very early on, we said we want to be able to easily extend it with new features, try out new things, and even if they work only with a subset of the existing methods, we will accept them if someone finds them usable. In Fluxo, this is a little bit different. So in Fluxo, everything has to work together with everything else. So this also changes this a little bit. Overall, however, I would say that the line count in Trixie is probably a little bit lower than it is in Fluxo.
All right, thanks for the answer. Any other question? There's one more from Johannes.
Hey, actually, can you hear me? Okay. So you were staging to temp, and I'm curious, did you try a container runtime, and if so, what were your experiences?
So question is, did you try container runtime? What were your experiences if you did?
No, so far we have not tried to use Trixie JL within a container runtime. No.
I have a question. I can go here. You mentioned parallel I/O. What are you using currently for parallel I/O?
At the moment, we're still relying on HDF5 JL. Because we had prior experience with that, and admittedly, it has not been our main focus so far. Because as you saw from this presentation, we're just getting into that regime, beyond 10,000 MPI ranks, where parallel I/O becomes really a key issue. So we're just starting to dig into this. One thing I definitely want to try out is to have a look at Adios 2, maybe, because I think it can help us in a few areas, but I haven't done this yet.
Don't. No, actually, no.
You said don't if you like.
No. Actually, do it.
All right. Anyway.
Well, sorry.
Go ahead, Michael.
No, I just mentioned IDSO because I have a good connection with one of the key developers of the Julia package, so I thought that might help.
Yeah, I'll contact Eric. So.
You'll contact Eric. No, thanks, guys. Thanks for answering the questions. Let's thank the speakers again.
Thank you very much.
Yeah, I'm glad that it worked out in the end. Let me go over here so that it's also recorded, I guess. So according to the schedule, this was also the general Q&A for the first part because of the technical issues, but I guess that's fine. So now we have like I think 10 minutes break scheduled. So we'll reconvene at 11:40 for the next talk, which will be by William, I think. All right, see you guys.
Yeah, I may try and go inside.
Well, I reduced it. Oh, you did? Have a look. It's hilarious. So, I don't understand. The fun thing is... Wait,
Ja, das wurde ja, gut, dass am Ende noch geklappt hat. I get to see it right now. Like it was like every time that what's the technical issue? Both of it. I've always wanted to try it. Well, actually,
in my code that special collision path. And I guess from the I wouldn't be because a bunch of things are like, oh, it works very well. The main one no, but then it's not
Hello, hello. All right, everyone. We're going to continue in like 30 seconds or so. We're going to continue in like 30 seconds.
Yeah. We're gonna start again soon.
All right, so I'm happy to get started with the second part of the mini symposium. Our next speaker is William Godoy from Oak Ridge National Lab. He's a senior computer scientist, and well, he has been the main developer of AGS2, by the way. So for those who didn't know that, that's why we had this little discussion before.
Well, thank you very much, everyone. Actually, it's good to see everyone in person, and very proud of this community because we've been very busy in the last couple of years. So, as Sam mentioned, my name is William Godoy. I want to actually, I misspelled my name. So I'm going to talk a little bit about what we've been doing. I purposely removed the summit part because my hours were gone. And now we're back to the x86 world, so with powers of 2, number of GPUs and nodes. So the good news is that we got access to Frontier and Frontier hours, and, well, I'm going to share the news. I want to thank the contributors here. We've been working very hard this summer with my interns, with Pedro and Jeff, and try to understand what's the value that Julia is bringing to our world, to HPC. So that being said, let me start. Well, first talk about the motivation, right? This DOE HPC facilities, why, we have them, and why the government pays for such incredible facilities. I'm briefly going to mention the Julia value proposition, the way we are trying to frame the message to the HPC community, who are not necessarily familiar with Julia. Then I'm going to go and share the results on Frontier of what we've been doing this summer, trying to make sense, see where we are as these machines deploy. For those who are not familiar with Frontier, it's the first exascale supercomputer deployed in the world. I'm going to share my conclusions and final thoughts. So the motivation, just to describe, our U.S. Department of Energy computer user facilities are heterogeneous GPU accelerated systems. I'm closer to Frontier. I'm not at the facility, an organization, but we work closely with them. Johannes here is a nurse. He can talk more about that. So reach out. We are very, very open to share, and we try to close the gap between universities and the private sector. And we are hiring too. So if you're interested, check it out. We're always looking for good people to collaborate, internships, different programs, as you can say. So we're moving into the exascale world. So we're deploying things like Frontier, Aurora, Perlmutter. So a lot of what we do is driven by and funded by the science. So I attach a link if you want to know more about national labs. I put this slide because I purposely want people to inform, hey, this is what we do. There's not much knowledge about what national labs do. I'm sharing with you, a graph from Wikipedia showing that, yeah, we're obsessed with GPUs. That's what DOE uses. But in HPC, CPUs are still very important, right? As previous talk showed. So we are very niche when it comes to HPC. Even HPC is niche, but DOE HPC is even more niche in that regard. Top 10 in the top 500, or why not? So one of our requirements, for example, is to have performance portable layers, like Cocos, Raya. DOE pays for these kind of things, kind of like Adios as well, right? Trying to be a performance portable layer, not for the general computing world, If you want to understand more about, the landscape, I highly encourage you to read about this paper. It came out last year. It's very interesting because we have to rethink what exactly we're doing now that, we're hitting energy limits and whatnot. So, and that's part of it, right? Part of the Julia appeal is that, okay, we need to rethink how we're doing computing. One of my favorite quotes from Bacchus, it's unfortunate. He wasn't solving just a technical problem, but economical problem, right? So we still use Fortran. It's heavily used in HPC. That's not going to go away, right? But now we have heterogeneous computing, and we need to get to an answer quickly. COVID happened. Okay, how does this big iron that we pay can help us solve a pandemic, right? You cannot port all these legacy codes right away. So this is just to motivate the audience. So the way we're trying to frame it with this community, part of our conversations for a couple of years, that we don't want to sell Julia as, oh, you're replacing Python. No, you're really replacing the process that goes from idea to paper, right? If in HPC, because HPC, at least in the DOE, is very motivated by the science that comes out of it. So if we can put that in the community and they understand the value, and why not, that I think is a selling point. That, you are going to get into an ecosystem and a community that thinks like you, aligns with what you need. So going back to the technical point aspects, Frontier is a top priority for us, right? First exascale supercomputer, AMD, it's a newly deployed system. We have Lumi in Europe, so it's getting into the, top HPC market. I'm listing just the characteristics about it and how the architecture was deployed and what is it that we are targeting. These are really experimental machines at the end of the day, right? We have to produce software for the hardware. So this is part of our initial evaluation. Before we even go into Frontier, we start testing, as a previous speaker said, we have to test on-node scalability, right? How does this thing run on the GPU? GPU is driving the compute power. 97% of the compute power is coming from the GPUs on these systems, right? So we actually published a paper that got accepted at the IPDPS workshop, and I shared that with Valentin, and he co-authored that paper with us. And we see that, wow, Julia's in a very good position, right? There's gadgets, of course. We're not going to claim that this is 100% perfect. So for example, and I checked with Valentin, it was like there was some compiler optimizations MBHPC was doing that, we didn't know about and all that. AMD GPU was, pretty great, but this was a very, very simple kernel. The paper is there, the code is there, and all that. This is just a matrix multiplication, manual matrix multiplication, not even tiling or anything. Great news, FP16 was supported out of the box. So, this is just old news. I'm gonna share with you the good news, the new news. So we have then we ask, okay, we have simple kernels, but what about the workflow components? Can we write all of them in one language? Because ultimately, we have to care for the MPI communication, for the parallel I/O aspects, not only for the kernel computation, right? Are we memory bound, compute bound? It becomes, more convoluted. And what I'm showing here is a typical, just like the previous speaker show, right? It's your typical diffusion problem. We add some random numbers and why not? Ideally, you want multiple backends to tackle this. You want to run the CPU and GPU. Then you want to go into the computation, do your loop. This is, if you have done computational physics simulations, this is very familiar to you. If you're not, then you're feel free to dig into this material and we can talk offline because there's parallel I/O, things like that. So you solve your PDEs, right? And can I write my data analysis in Julia? Can I write my simulation in Julia? That's kind of where Julia wants to be, right? We use this material for tutorials and those kind of things. So going back to the computation, the stencil. This is a typical 7-point stencil because, as you can see, it's a 3D problem. And this is a fundamental kernel for CFD computations and typical heat transfer, typical problems that occur in science and engineering. And as you can see, they're not necessarily, there's some penalty, right? Because you're accessing memory from far away areas. It's cache friendly when you collect your neighbors. So you can get some measurements. The measurements that we actually chose is the bandwidth on the single GPU. So we compare, why? Because there's also AMD code that is available. They claim 800 gigabytes per second on an MI250, but when we run it ourselves, you know, we only got to this number, 600. So this is important number. Now with Julia, it depends how you look at it, right? Is the glass half full of, you know, half empty? We got, with a dynamic language, we got very, I mean, half the way through. Like, I think it's good news on a very experimental machine, right? We still have to learn more about and understand what's going on. So by bandwidth, I mean, because this is a memory bound, you're always going to have your bottleneck of how much memory you are accessing, right? This is a stencil for those who are not familiar with those loads. And we also measure the actual data movement. There is the effective one, the theoretical one, but there is the actual one that the profiler can give you. If you look at the profiler trace, this is your typical, like, oh, do some computation, fork join, you know, flow. Do some computation, stop, do some MPI communication, stop, maybe do I/O here and there, you know, and then go back to your next step. So this is a kernel, and let me address this. So we look a little bit further, deeper on the lower levels, and we say, oh, well, you know, Julia is doing the right thing, because this is driven by the number of, you know, stores and loads at the LVMIR level. And we're like, okay, this looks great. Maybe it's AMD doing something we don't know. So, you know, so kudos to the Julia HPC community maintainers, and, you know, we'll keep the conversation going. Also, we measure that bandwidth, you know, on node scalability as, whoop, what happened? Something just went away.
It's back. Oh, there. It's back.
Oh, okay. Sorry about that. So, oops, but not here. Up. So we want to, what happened here? So this will be good enough because I have to move. The JIT, right? That's an amortized cost that you're always going to pay with a dynamic language like Julia that compiles the first time. So we have to measure that. Once you run to 4,000 GPUs, of course you're gonna feel it. You see, like, it's kind of 1/10 of the performance. But the next time you have these two peaks. And this is, well, I mean, our smart guess is that, oh, because the boundary domains are not going to do as much work as, you know, in internal domains. So this is a typical trace in this type of large parallel problems. So we also run some weak scaling using this grayscale. As you, we imagine, as you increase the number of nodes and communication, you're going to have more variability. So, you know, but we tested it successfully at 5% of the machine. Once I tried half of the machine, of course, it didn't work. Some MPI issue there. And, you know, I just want to wrap up here. Conclusions. I want to thank my intern, Kyra, who's in the audience. She did a lot of the work here. Julia's current 50% of the GPU performance on a memory bound app that is, you know, typical and important. The scalability is still subject of, is this a machine? Is this the software? Is this the hardware? You know, we have to find out. But another important thing is that community is essentially you. We, as I mentioned, we run a lot into different activities. We're also looking at generative AI, how is helping us, because we have to work nicely with the next generation of people that will use these things, you know, to program, to code. I want to acknowledge my sponsors, and also especially our you know, package maintainers and developers in this community who make this work possible, you know. All the underlying works. Many of you are in the audience, so feel free to reach out to them. And if I miss someone, let me know, because I want to put their names on that. Selfless, shameless self-promotion. We are organizing a workshop on supercomputing, on democratizing HPC, which I think that's a message that Julia encapsulates. So thank you very much.
All right, one very quick question, maybe, if somebody has one. If not, then we continue with the next. One, yeah.
Have you been using the matrix scores of MPGs? Do you have any experience on that?
Question is matrix scores on What's this one again?
Right. So that's a great question. No, we haven't, but ultimately, because the stencil is not, optimized for that, but we can easily call like optimize blast under. That's the beauty of Julia, right? It doesn't reinvent the wheel. If you have an optimized blast, then just might as well use it. But thanks.
Let's thank. Sometimes it doesn't work. Okay, now let's thank the speaker again.
Okay, the next speaker is Mose Giordano, Senior Research Software Developer at UCL.
Oh, do I? Oh, this one. Okay, perfect. Thanks.
It's there.
Yeah. Okay, if I do this.
Can I see that? So.
Yay. No. Yes. It works. Cool. Okay. Okay. Can I go? Okay. So hello, I'm Mose. I'm a software research software engineer at UCL, and I will talk about using Julia on the former fastest supercomputer in the world, which was Fugaku. So this was a work that we did last year with together with Milan and Valentin. And so what is, first of all, A64FX? So A64FX is a CPU. ARM CPU uses the ARM architecture. It has 48 cores, and it has native support for floating point 16 bits, which is something new in the HPC domain. And one very special feature of this CPU is that it has the scalable vector extension, which means that the vector extension is not fixed. The vector width is not fixed, but it can be variable. And this is chosen at runtime by the processor. And Fugaku was the first supercomputer to use this CPU, and it has been the #1 in the top 500 for a couple of years before Frontier was put online. And this is powered by 158,000 processors for a total of 7.6 million cores. And what sets Fugaku apart from the rest of the most of the other machines in the top 500 list is that it has no accelerators. It uses only CPUs. And if you want to know more about what I'm going to tell you about in this talk, you can read our paper just in time. It was written in 3 days. Yeah, so there will be more details, but let's see. So we did a performance and scalability analysis of Julia on Fugaku. So first of all, we tried to define a function, a level 1 plus operation, which is AX plus AXPY, which is a scalar times a vector plus another vector. And we compared this, the function written there in Julia, like couple of lines of code in total, basically, and the blast functions provided for by the vendor and some other binary implementations that are available in the ecosystem. And for this, basically, we are using here this function in Julia, which lets you call blast functions in external libraries. But Julia has this feature, it's called a blast trampoline, where you can choose which blast library to use. So we can easily test different libraries in this way. So here is the first plot, depending on the number of elements, basically, in the vector, on the vectors. We can see the speed of these operations, and the Julia line is the blue one. So higher is better, and you can see that it has the best peak performance, and for the rest is usually comparable, competitive with Fujitsu Blast. Fujitsu is a vendor of A64FX, so it is competitive with the Blast provided by the vendor. Yeah, and also Bliss is another high-performance Blast library, and again, this is usually comparable, especially at the higher, larger number of elements. This is using single precision, so 32-bit floating point numbers. We did the same also for double precision with 64-bit. The plot looks pretty much the same. Again, Julia gets actually the best peak performance. In this case, actually, Fujitsu Blast has the best performance for larger elements, but still very close to Julia as well. And then we also did the same experiment for half precision, but unfortunately we don't have the implementation of Blast in half precision for any other libraries. Instead, in Julia we use the same function for everything. So this is, again, the performance. It looks pretty much the same as the previous plots, but the higher, larger vectors are not as flat as before. But anyway, so we don't have any reference for the others, so this is the best as you can get anyway. So shallow waters, I think it was mentioned already before. So it's a code by Milan for CFD. It's written in Julia. Most importantly, it's type agnostic. So this means that you can use whatever floating point numbers that you want, including half precision. And yeah, Milan ran this code on A64FX. I don't think it was Fugaku, though. I think it was Isambard, right? Isambard. Yeah. But yeah, it's another machine with the same CPU. And so he found that this provided a 4 times speed up compared to using double precision, which makes sense for a memory bound problem because you can put 4 more numbers basically in your operations. And the qualitative results of using these is pretty much the same as floating point of double precision. I guess a caveat of using low precision is that you need to scale back your problem, like scale down your problem in order to be able to do all your operations in a meaningful dynamic range. So it's not that you can just do any operations in a single half precision. You have also video to show the comparison between, I think, double and single precision. No.
But it says double and half precision.
Yeah. This is better. No! Is it okay? Okay. So you can see the comparison between double precision and half precision, and qualitatively it's basically the same. Again, but you get 4 times the speed. Cool. Next one. Again, this is the comparison of the speed. I think. Sorry, I don't see the plot here. So higher is better, probably, yes. And half precision is the red line, yes. Inside this one is single precision, and this is double precision. So, yeah. Another analysis that we did on Fugaku was comparing performance of MPI operations, just pure MPI, just communication without any computation going on. And this was done like this. He's like one kernel, MPI kernel looks like written in Julia. If you're familiar with MPI, writing in any language is pretty much the same. So MPI.jl is a package which we use for doing MPI communication in Julia. It has to deal with many different MPI libraries that exist in the world, which is very painful, but yeah, it works, and we can do some performance comparison. So this is possible because Fugaku, the RIKEN, the institute which runs Fugaku, provides the reference values of the MPI communications. So here I'm comparing the performance that I measured using MPI.jl with the results from the RIKEN benchmarks written in C. This is the time, so latency of the communication ping pong. You have 2 nodes and send one message and receive one message back. There is some small overhead for smaller messages, but for larger messages, it's pretty much comparable. And we have also the throughput, yes. So throughput is basically the inverse of the previous plot. And you can see that actually when you do MPI communication, anyway, you want to use larger messages to get better throughput. And Julia is within, I think, less than 1% from the recency in benchmarks. Other benchmarks using MPI already use, again, some small overhead for smaller messages, but then it is pretty much comparable. Yes, this is using 1,500 ranks on 384 nodes. Another command getter the. So this is fun because Julia looks like a lower latency. 1 minute? Okay. Looks like it has lower latency. I think there is a problem with caching here because we don't do, in these benchmarks, we don't do cache avoidance. Instead, they do implement cache avoidance in the C benchmarks, and the cache size of A64FX is exactly 64 kilobytes. So my guess is that we are doing some weird caching here. I don't think this is real, that Julia's poster. Last benchmark is memory bandwidth. This is done on Okami, which is another system, not Fugaku. Using this EXPY program. So Fugaku, A64FX has 4 NUMA domains, so we are doing the same runs in using different numbers of NUMA domains, so 1, 2, 3, and 4. We expect perfect scaling. It's actually very good. Up to 2 domains, there is a small drop of performance for 3 and 4, but this is comparable, especially for 1 and 2, it's comparable with similar benchmarks that have been done in C on the same CPU. So this is the conclusion for this work. So Julia is not especially optimized for A64FX, not at all, but get very good performance thanks to LLVM. Compilation latency on A64FX is very painful, and this is especially bad for a JIT language like Julia. Julia 1.9 has caching of native code, which kind of reduces the pain, but pre-compilation takes even longer in 1.9. So there is this trade-off. There is one caveat, is that in MPI, custom reduction don't work on non-Intel architecture, so this needs someone to fix this. And Julia has a native support for half precision floating point numbers, and actually thanks to Gabriel, also on AVX 500. And I think that's all. Thanks.
We have time for a couple of questions.
Hello, thanks for the presentation. Just a simple question. Did you perhaps measure, informally perhaps, energy consumption on the CPU?
So Fugaku, when you run a job on Fugaku, they do report memory consumption. I don't have a good reference with anything else. So I have some numbers, but I cannot tell you it's good or it's bad. So they do share in the statistics also what's the ideal memory energy usage for the job, and I think usually Julia is within the ideal memory energy usage. But again, I would have to do a similar workload on C, C++, for example, to say, oh, Julia is okay or not. I don't know.
I was asking actually comparing to x86, but thank you.
Well, ARM in general tends to be less energy angry.
Thank you.
We still have time for another question.
Thinking forward to, does this work? Yeah. Thinking forward to other ARM systems like Grace Hopper, I guess this is good news that Julia seems to perform well on ARM.
Mm-hmm. Yeah, again, this is all thanks to LLVM. We did nothing special for this. So yes, the vendor support for LLVM is very important.
So I guess my question is practicalities is, are we going to get ARM 64FX CI infrastructure for? We have to add to the stack of minis, Mac minis on the.
Given the time that it takes to compile.
Well, it's actually more serious. Like, actually, like, are there outside like these centers? Are there ways you can get access to 64, like, to these machines, like these boxes? Or, like, do cloud providers provide you instances or these sorts of things as well?
That I don't know. Okay, good.
So AWS has Neoverse 3 that you can spin up, and if you
personally want one, it might be the best thing to buy a Mac Mini and then install Linux on top of it.
But you don't have SV, because what's cool about AS648 is SV. But MacBook has a half precision, native support for half precision, which is very cool. Okay. Thanks.
All right, let's thank again Jose. So our next speaker is Carsten Bauer, he's from Paderborn Center of Parallel Computing. He's a HPC advisor, senior HPC advisor.
Thank you, Sam. All right, I think we're good to go. Yeah, I'm Carsten. I mean, you've heard me speak before, if you attended the first part, at least. I wanted to take that opportunity to talk a little about HPC tooling. So HPC tools for Julia, how they work together. I'll talk a bit about specific tools that we develop, but also mention some other ones. We had some great talks about them as well. I mentioned a couple of those. And yeah, that's what we're up for in the next 10 minutes. First, let's start with the obvious. I think we all agree we need good HPC tools, right? If we want to take Julia seriously on these clusters, we've seen, massively parallel applications, Trixie. We need good tools to understand what the ranks are doing. And there's a good news, right? We want to, first of all, we want to profile, trace, maybe even parallel debugging, all the good stuff. And there's a good news, which is obviously there's lots of great HPC tools out there. Vendors, not vendors, mostly HPC centers, but to some extent also vendors have developed, multiple tool suites for profiling and all the things. And I show some plots here, and the first three at least are actually Julia. So I used tools to analyze Julia code. I'll talk about at least one of them in a second. There's one problem though. And that is, if you try to just utilize them, they often don't work, or at least not out of the box, right? So sometimes it's easy. You just have to write a wrapper. I'll give an example of a tool where we did that in a second. Sometimes it gets more tricky. You have to, modify the Julia internals to support them properly. And sometimes they're just fundamentally incompatible because they just target a certain language and that's it. Like they analyze the source code on a syntactical level or so, where you basically have to collaborate with them to make it work with Julia. As I said, I want to talk about a few tools that we developed at PC Squared, but again, in the process also mention some other tools. And we have more than those. You can check out the link afterwards to see what we are doing. The first tool I want to mention is Liquid. So Liquid is a low-level tool which allows you to monitor hardware performance counters in CPUs to get like a very low-level understanding of what your code is doing. So I show a little example on the right. So you have a multi-threaded XSpy. So it's the same operation that Mosi was just talking about. So DAXSpy is just the D is just double precision. And what you get if you use this perfmon macro, you get returned performance metrics. So it doesn't just show you some counter values, which might be hard to understand, right? But it gives you like understandable, like the bottom table, understandable things like runtime, double precision, megaflops per second, right? Vectorization ratio, like how much of my code was SIMD'd properly, and so on. So that's a very low-level tool that we built. It was just a wrapper on top of Liquid, the same named tool developed at a center in Erlangen. And the good news is that since we are doing Julia and we're greedy in Julia land, right? We want interactivity for everything we do. So this tool is interactive. Typically it's a command line tool, but in Julia obviously we have a macro, so you can run it in a Jupyter Notebook or Pluto even or whatever. As I said, this is an example of one of the things that worked out of the box in the sense you just had to wrap the C library, the shared library, and then there were some issues. So calling the tool wasn't made to be actively used. So calling some API functions twice just segfaulted, right? Because no one did this from the command line. But fortunately, we have a good connection to the Erlang people. We could work around this. So overall, a good experience. It's not portable yet. Because they hard-coded some path. Again, I'll try to convince them to help us get a JLL out. But overall, it was good. Let me mention some alternatives. Obviously, there's Linux Perf, which is, is an interface to the Perf module in the kernel. There's Papi, which I guess is like sort of the American pendant of Liquid. At least that's the way I like to pose it. And yeah. I gave a talk about Liquid last year, so a full talk. If you want to learn more about it, feel free to check it out. Another tool that we developed is thread pinning, right? In fact, it's also a tool that Mose used in his last talk for the DAXPy to pin threads to NUMA domains, right? So that you can know what you're doing. So thread pinning is a tool we developed for that. Pin your Julia threads to specific cores, to NUMA domains in a round-robin fashion or whatever. Also query and visualize your system, right? You want to know what you're doing. You want to check the threads are pinned correctly. All the good stuff is in there. How did we do it? Basically, we just call into libuv and libc, to get the current core, set the affinity, right. Currently, we use LSCPU to gather the system information. HWLOG backend would also be thinkable. I chose LSCPU for no good reason. It works fine. I don't see a reason to change it right now. Limitation only works on Linux. Windows PR is there, but I mean, we are at a Julia HPC mini symposium, so I guess that's no limitation after all. Again, I gave a talk yesterday about thread pinning at this JuliaCon. Feel free to check it out whenever it is online. Just some impressions I also showed yesterday, pinning cores, pinning to sockets, pinning to NUMA domains, right? You get all the nice visualizations. Again, you can all do this in a Jupyter notebook, in a Pluto notebook, so for a class, that's good stuff, I think. And yeah, if you do it right, you can get some great speedups, right? So I had performance tuning in my talk. You see, if you use thread pinning, I don't promise anything, but sometimes you get 8 times performance improvements if you have the right number of threads and all other conditions. And in parallel stencil, I made a PR, so that's the work connecting to the work that Ludovic was talking about earlier. There, I just took one of the examples that they have, like an acoustic wave simulation, pinned the threads, and so on. And there, I got a 2.4 times speed up just by making sure that everything is pinned correctly. Right. Another tool I want to talk about is MPI profiling and tracing. So there's ScoreP, which is a bigger tool, well known in Europe, developed by multiple players. One of them being the Jülich Supercomputing Center. Which we've also heard about multiple times before. The Eureka system, Joule system, was mentioned earlier by other speakers. And there I also wrote a wrapper for ScoreP, which is this measurement infrastructure for profiling and event tracing. So basically a tool that records everything, right? Like records the MPI calls, and it hooks into the PMPI interface, like the profiling interface of MPI. And I wanted to use it with Julia. And there I had a little bit more issues. So first of all, Julia has no tracing API, right? So I said PMPI, so you can easily hook into all MPI calls that are made by an application. There's like in the standard, there's an interface for that. But if I want to just measure all Julia functions, right, and give you a nice table of all your, it's going to be tricky, right? We have to rely on user instrumentation for now, right? You basically have to manually annotate things because there's no tracing API. Something we definitely need at some point, I think. Cassette is currently the workaround, right? So cassette gives you that overdubbing mechanism, so you can basically use it. And some people do, MPI tape, which I might mention if I have time in a second. X-ray, right, also currently relies on that. Again, similar to ScoreP, roughly speaking, a profiling tool. But it's a workaround because, cassette comes with performance overhead, and I think we can do better, just have to do it at some point. Right, and ScoreP is really, don't look at the code, I would say, because the problem there is they rely on LDA preload, and you have to actually compile based on what the user wants to measure, like so dynamically chooses, you have to recompile like a little shared library. So whenever you do this, like in the package, compile that library for you, then LDA preload it, and then with execv replace your current Julia process by a different one without you noticing. I made it the way that you literally don't notice. If you press Shift-Enter, it's like it seems like nothing happened, but I tell you it was black magic under the hood. And right, but it works. I'll show you some plots in a second. Alternatives. Simon gave a great talk about NVIDIA Insight Systems and NVTX, which is the instrumentation framework, yesterday. I think that's the most, much better tool right now for the job, right? So if you do something serious, use this instead of SCORP. I hope to get it to a better state, but it's currently experimental. Again, check out Simon's talk, was yesterday at this year's JuliaCon. Right, the good thing is, so I talked about the black magic already. Again, you don't notice it. You just put using SCORP in it at the top of your file. Then you instrument your code, like my region or whatever. And the reason I wrapped SCORP was that eventually it just produces two files, like a cubex file and an OTF2 file, one for traces, one for profiling information. And these are common formats that are supported by all kinds of other HPC tools, like visualization tools. You know, you can hook into all these other tools. Once we have that, we have like a lot, right? We have different graphs, 3D graphs, and all funny things. So that's why SCORP is, you know, one of the things that I target. And just to give an example, right, the profiling view you could, for example, visualize with a tool called Cube. You could also use Paraprof from the Tau toolkit. The traces you could open with Vampire. That's what you see here on the right. But you could also use the Intel Trace Analyzer. Again, once you have that format, right, you can plug it into different tools. That's good stuff. And if you zoom in on the right thing, we also have source code information here, right? Which is, again, is not trivial because how do you propagate that information? Those tools don't support Julia syntax or whatever, right? They don't look at the code in any way. So here I just have that as part of my macro, right? So I can just put it in. I think Simon does a similar thing with NVTX. Right. All right, I think I'm running out of time, but let me just quickly mention MPI tape. So MPI tape was born out of a very simple idea. We had a class, Introduction to High Performance Computing, which actually uses Julia, so for the first time. And there we want for, basically only for pedagogical reasons or educational reasons, we wanted to track all the MPI calls, visualize them in certain ways. We weren't sure even in what ways we want to visualize them. And so I used cassette, again, that's the workaround we currently have to just track everything. So I just track all the MPI calls. You can basically think of it as PMPI, just self-made on the Julia level, right? So not hooking into the on the C level into the well-defined MPI profiling interface, but just my own interface on the Julia level. Advantages: I can do everything in Julia, and it produces files for every rank, right, which contains all the stuff. You can even track arguments and everything. You have full information, and then you can visualize it. So here I show a combined tape of a simple thing, different colors or different ranks. You see the sends and receives, who talked to whom, and so on. So I hope that there are nice, you know, possibilities for those kinds of tools. And just as a comment, Simon and I talked about this, right? And a cool thing would be if you could replay everything. Since you have recorded everything, you might want to replay it and then say, I want to be on rank 5 with an interactive REPL, right? And the rest should basically mimic the real run of the application. So we have lots of ideas there, but only limited time. And final slide, tracing API, I want it. I don't know who's going to provide it, but I'm on board, at least to help. We need common instrumentation so that all the bunch of packages that we have, essentially, it would be cool to have just one macro and then you can switch the backend, right, so that you don't have to instrument the code multiple times. User documentation, more tools. There are lots of out there, lots of work to be done. That's it, I'm done. Reach out to me. Thank you.
We have time for a couple of questions.
Tau. Have
Yeah.
a look at Tau and probably make it part of this set of backends that you're.
Yes and no. So I looked at it and I didn't do any work on it because, I mean, the frank answer is obviously I have a German bias. I work as a German HPC center, and you know, SCORP is just right. Not next door, but sort of next city. So that was for strategical reasons, my first choice. But I'm not opposed to doing anything with Tau. And also the documentation I found at the beginning slightly confusing. I've never used Tau before. So SCORP was much better documented. Yeah, but no good reason, so I'm open for it.
Okay. Yeah. They're very also willing to look into Julia from there. Side.
HPC toolkit is another thing, you know, with DOP. But, yeah. DOE.
In general, I'm interested in correctness tools for Julia. So one would be, there was a tool that my co-advised students presented yesterday called Float Tracker. That is
I
for
attended the
floating
talk,
point.
nice talk.
Yeah. And the other wish list I have is data race checking. Do people complain about data races?
Yeah, funny that you mentioned it. Data race checking. There's a tool in Germany called Must. I had never heard of it before. Maybe that's on me, but I attended. I gave a workshop actually, and one of the authors was in the room, and we chatted about it. And obviously, the first thing you do is you try it out, and it already works quite well with Julia. There are some rough edges where we could. Yeah, and so yeah, I'm very hopeful because they also rely on LD preload. Yeah, absolutely. I fully agree. Again, the list is long, right? And if anyone wants to join the effort of supporting these tools, feel free to reach out.
So Julia-based does support TSAN, ASAN, and MSAN. There are lots of interesting questions around deployability and how you make it easy for users to use and how you give good answers back that users can act on.
Yeah.
But the tools are supported.
Yeah, must spits out an HTML table, I think, right? And then green color for you did a good job, and red color for something's wrong, and yeah, kind of. Again, I'm not a must user, but I've played around with it.
Okay, let's thank again to Karsten. We have now still 5 minutes for a little Q&A about the whole session. If there are more questions to bring up, could be about anything.
So actually going back to the API, because this is very important, right? Having a working
You mean
group,
the tracing API?
The tracing API profile, having a working group that is dedicated at least to have like some sort of spec, I think it's worth it from where we are now. What do you think?
Absolutely, and I have one more reason. Python have it, right? Obviously, they screw performance. I mean, they have a problem. It's not even a race, but they have it. Like I think there's the sys set trace or whatever, right? So you can just basically hook into everything.
Should we just steal the API?
Yeah, we are more greedy. We want to have it efficient. We have cassette, right? We want to be more efficient. Like, yeah, I don't know, Valentin, you have a...
So one question that comes immediately to mind: if you want to trace everything, do you want to trace? You want to obviously say every Julia function call want to be traced.
No.
Well, Python can do that because it's interpreting, and every function call is costly.
Yeah.
In Julia, we do inlining, we do optimization. So what happens in those contexts? Do we want to make your code a lot slower?
Yeah.
Or are we okay with losing some information and making your code only a little bit slower?
And the related question is, well, could you annotate specific functions and say, I want to trace these functions, but you know, typically it's going to be like the high-level ones, but you don't, the interior ones are not. Yeah.
Yeah, as a specific example to support Simon's point, if I may, timer outputs, right? What lots of people do is, I've seen it multiple times, they write macros that they can annotate their function definitions with, so sort of get auto-annotation in a manual way, right? Like even something, there might be a middle ground, right? That yeah. You want a photo session?
Yeah, photo session at 12:30 on the lawns.
All right.
As soon as the stock is over.
All right. Let's stop it here. We have plenty of talks. There's above tomorrow, right? Another session after the break. Let's take a photo together.
Boom.
We need more caffeine.
Absolutely, it's good.
Yesterday I woke up at 4 in the morning to catch a plane. Yesterday we were like drinking at night. I feel like if I sit down, not because of the talk, but I'm showing age.
Within 10 years, we can show
So
up.
you do everything in one big bang.
Milan, yalla, yalla.
Collection of tools, a nice talk.
Sorry, I'm trying not to be late on that. Extremely important photo session.
Even just the print line that the spacing looks like the new JuliaCon. That has exactly the distance, the old one is exactly what you would get from a evaluation.
Some system that showed up my name, that's, there's no,
Yeah, so like, so his computer, like, you think went to sleep the second
I
time?
don't think that has anything to do with that. I think
Yeah, I don't think.
Splitter
It
cut
couldn't have
plug
anything, yeah, it couldn't have anything to do with this, but just when I pulled that, like, I saw that go up, I was like, connected to that thing. But it was like, I was looking because the decimator, like the top line was saying no signal. And I was like, is it something with this cable? Like, so I went to reseat it, didn't change that. No, it was just like the second that I went to do it, you know. So here's my other thing, you know, all these people coming in here like this, and it's like, I left a couple of spaces like right here so that there was room for people to move around the camera without it. This seems to be the most popular space, you know, everybody's got to sit right here.
You know, they see a space.
Right, yeah, well, here's where the spaces are now. It's over here, you know.
Need to put a rope line.
Yeah, there's no chairs over here, so nobody comes up this way, up to the front, so. You know,
That's one way of doing it.
fucking joke. You know, it's just, it's silly. Yeah, I'm gonna put a guy right in front of this guy, he'll probably come back to that spot.
The fiber was fine, it just got.
Yeah, you know, well,
Got spun
you
by
heard
it.
those guys over there like banging around trying to get in this thing, and then when I looked, and the thing was under the chair. I think it was under, you know, here, but it's like, if it's sitting right on this, it's like, yeah, these HDMI wires are, they're not as robust as like SDI or, you know. So when I saw that, I'm like, how would happen? Because that's gonna suck. Anyway, I'm glad it was just a disconnection thing, but I was like, what the, you know, everything's been working fine. I don't know, fucking guy gets out there. And it's like, what the hell? Anyway, by the way, I saw this, is this yours? Like, or, you know,
That's it, that's it.
Oh, just
the pack.
you can leave it on this cake, on here or something. I saw back here, I didn't know if it was somebody in here, and then I said, oh, that's an
I
unique
just
thing.
brought this thing up here.
Yeah, no, that's cool. Yeah. Go for it. Alright, I gotta make a phone call, so.
Hi, this is Win Plumbing. Yeah, I'm calling for my folks. They live at Edgehill Avenue in the Bronx, and they need a new hot water heater. And I'm trying to find a plumber that might be able to help them.
like multi-layer. So the bottom layer is we're trying to capture people's data types. That's like pre-baked like vector abstraction right there. And then utilize them for their necessary idea for indices and data in a stored pattern. So if you say sparse, like we know that there's going to be we split it into blocks. Blocks are zeros and blocks are numbers. And then the next layer up we have people like tensors, which have unique ID numbers, and you can just then graphs the next level. I use like create backend portion, and what I've done recently made it possible for you to just say, okay, make an tensor and then wrap it a cool array, or you can do cool and it calls. So similar idea with AIM, but I noticed like schedule everything, like a little sketch we talked about, right? To have sort of with like you had like the schedule and basically like pencil sketch and the graph. I'm wondering like, so if I want to use AMP, and I let users say, okay, just like convert the backend to AMP. What happens if I do something like I want to call a job? Like do they also need users to like create this, if it's multi-user, then even they have the environment where they say, oh, so can I do that in a dynamic way? Is there something that AMP already does? Yeah. Because like one idea is like what OpenCI does, or people have scheduled a free. It's like so cool. Yeah, send it to their. Yeah, that's what I'm here to watch. So like those, that's really where you can like Is it going to be bad, like if we do something where, if we want to be distributed, create multiple MGGPs that get created on whatever process, just like, what if we do that and then try to run it like a Yahoo and do my output that does it correctly?
Yeah, that's what's good.
Well, I mean, the hackathon tonight, but these hackathons
Yeah, because I talked to Valentina and Moses in order to talk about the extra.
I think he meant
okay.
I don't think he meant
Yeah. Okay, great. Yes. Right now, there's no like
we just need to first be able to have those packets. So like right now we can just make a small addition and then make it possible to use it. You can build it into whatever, if you have your algebra thing or any all these things that they will call yours. But do you have things like
What I would say here is I have these two configurations,
I've implemented that right now. But
so did the Julia SDKs take like a pain? Just because we don't currently so there's a kiss get bracket and that's because like I thought about adding something like kiss get to bracket Julia, but it's not letting me ask. But if somebody else wants to write something,
No, yeah, I agree because
Like yesterday,
I'm
it's
doing
not
what
great.
you put the community down there, like, something like first. Yeah, and probably my like if I put like
Yeah, I mean, the easiest thing I can do is not only get them making block
yeah, like something that
oh no, I agree.
private
So do you think like we'll truly need to be able to one rate general which can be specialized by the right? Do you think it's necessary to like capture all these different things with the half scale rate, all these back edge rules?
So they have some ways you can do this for all these different honestly, one of them, like, the simulator isn't that
So if I multiply and let me
This one, I guess. Oh no,
This one has HDMI as well. Let me just quit some applications so that I don't get notifications. Welcome everyone to the afternoon session. We have a nice program again. The afternoon session is a bit about the ecosystem development, and we have a great pleasure to have Tim Besar here, who has basically within his PhD created the basis of what is today GPU compiler and CUDA.jl. And so he is a software engineer at Julia Hub, and please go on.
Thank you. So I'm Tim at Julia Hub. I work on a variety of GPU backends, including CUDA.jl, Metal.jl, but today I'm going to give a brief overview of OneAPI.jl. So for those of you who aren't familiar with OneAPI, OneAPI is Intel's approach to cross-architecture accelerator programming. So in principle, they don't restrict themselves to only GPUs. OneAPI.jl, the goal of it is such that it can be used on a variety of accelerators, not only Intel accelerators. But right now, both OneAPI, the Intel project, and OneAPI.jl, our Julia package, focuses strictly on programming Intel GPUs. So it's one of the packages in a row to target one of the accelerator platforms that we have. Normally, OneAPI, it's an entire middleware, a framework. It comes with a C++-based programming interface. We, of course, replace that with Julia. It comes with a whole variety of libraries, like OneMKL, OneDNN, and so on. And it also brings a whole slew of tools to profile, to debug code, and so on. So on the right-hand side, you can see that we, with Julia, we offer a similar programming experience that we have in the other GPU packages. You can do direct programming with kernels, with a kernel dialect that, again, looks intentionally very similar to all of the other backends, so that it's easy to switch from one GPU backend in Julia to another GPU backend. And of course, we also offer the API-based array programming that makes it possible to write generic code that should theoretically work across all of our GPU backends. So OneAPI.jl has actually been in development for quite a bit, and development is also just happening steadily. In this talk, I'm going to give an overview of what we've been up to for the past year, and summarize that involves including supporting more hardware, supporting more Julia versions, adding wrappers for OneMKL, integrating with vTune, and a powerful kernel abstractions backend as well. So briefly zooming in on each of these, the new version, the latest version of OneAPI.jl supports a whole new bunch of things. Most important of which, I guess, is the support for the discrete Intel Arc hardware, which is a new series of GPUs you can buy and put in your desktop. So not only the integrated ones that we had been using for the past couple of years of OneAPI.jl development. The nice thing about the whole OneAPI setup and this discrete hardware is that the only thing it requires is a sufficiently up-to-date Linux kernel. So we can actually build JLLs that not only provide libraries like we do in the CUDA stack, cuBLAS, and so on, but we can also ship the entire user space driver, which is essentially libcuda. In the CUDA system, you always still require to install an NVIDIA driver. With the OneAPI system, the only thing you require is the Linux kernel. So that's definitely an improvement compared to the other vendors here. We now support 1.6 to 1.9, and 1.10 is also being tested by CI and will come with a nice 20% latency reduction. This, of course, isn't specific to not specific to OneAPI.jl, but nonetheless, it's a nice feature to boast with. Platform-wise, we only support Linux. Windows could be theoretically supported, but as mentioned in a previous talk, that's not really of interest to this audience. And if you really need to use Windows, I've heard it's possible to use our Linux binaries through WSL2. One of the more interesting features we added this year is integration with OneMKL, which should drastically speed up many OneAPI applications that use BLAS level 1 to 3. So the tricky part here is that OneMKL, the Intel library, it only offers a C++ API. And of course, in Julia, we're not good with C++. So sadly, we had to write C wrappers that wrap the C++ APIs of OneMKL, and we did that in collaboration with Intel. So now we have a C API that's very similar to what you might be used to in cuBLAS or in the CPU BLAS. We use that to create Julia wrappers, and then we integrate those Julia wrappers with standard libraries like linearalgebra.jl. Again, very similar to all of the other backends we've got. This, of course, also means that it might be a little hard, or it might take some more effort to integrate with other libraries, because the first step is always creating a C wrapper for the C++ APIs. And only then we can start working on the Julia wrapper. So that's why library integrations have been taking a little while longer, but they're getting there. What's also important is, of course, integration with vTune, so that once you've written an application in Julia using oneAPI.jl, you can profile the application. vTune could already be used in combination with Julia to profile your own code, but we've done a bit of development to develop Intel ITT.jl, which is a Julia wrapper to interface with the Intel instrumentation and tracing libraries, which make it possible to enrich your timeline trace in a very similar way like we saw earlier today with MVTX.jl. So I stuck to the Intel ITT naming scheme here, but the add task is very similar to arrange. Collect is the same as the add profile you have in CUDA.jl. So you have all of the same similar constructs, and as you can see on the timeline on the right, you can see my vadd range being annotated, and below that all of the API calls that happen on the host. To generate this plot, you can use the vTune binary with -collect GPU offload, and you start the profiler in a past state, because with the add collect macro, we started on demand. And I've recently written a blog post documenting this all in detail, because with vTune, it's also trivial to do this on a remote system and then copy data back. Again, very similar to how N-site systems work. And similarly as to this works, how N-site systems work, if you want to look into how a kernel works specifically, you can use the GPU hotspot analysis, which compares to N-site compute, basically. It does give you less information, but nonetheless, it can be very useful to figure out why your memory copies might be slow, or how a kernel is stalling or not when it's being executed, scheduled on an Intel GPU. And the final large noteworthy contribution or improvement is a kernel abstractions backend, which makes it possible to not only write vendor-agnostic array codes, but also vendor-agnostic kernels, as you probably all know. So what's noteworthy here is the performance of these backends being compared on the right. This is a diffeq workload from a recent paper. So as you can see here, obviously, CUDA.jl performs the best, especially so at lower trajectory count, which means when the kernels don't take too long, because CUDA.jl basically has been nicely optimized over the years, meaning there's no type instabilities in host code, there's no inadvertent JIT compilation being triggered, and so on. On the higher trajectory counts, where the workload is much higher, all of the backends perform similarly. But it needs to be noted here that the Intel A770 I used here theoretically should be able to offer twice the flop count as the Quadro RTX 5000 I was using for the CUDA benchmark. So there is definitely still at least 2x performance gap being left on the table. But the question is, who leaves it on the table? If it's oneAPI.jl or maybe the oneAPI libraries, that's unclear at this point. We developed the vTune integration in order to be able to debug these issues and improve oneAPI.jl going forward. There's also been a slew of minor changes that don't require an entire slide to explain. We have multi-device support now, again, in a very similar way to CUDA.jl, where you can switch devices and query the current active device. We support shared buffers, which is basically unified memory you might be familiar with. And we also have a nice debug mode, where if you toggle this, we'll download different artifacts from Yggdrasil, which have debug mode and assertions enabled. And this is very convenient in order to see some more details about backtraces or to check some preconditions when running code. This is strictly for using oneAPI.jl on hardware that may be unsupported, or where you may suspect there may be a bug in the backend driver. So going forward, as I've shown with the kernel abstraction slide, kernel code already performs reasonably well, but the array abstractions need to be optimized because many of these were developed for CUDA.jl, and even though we've ported them to the other backends, that doesn't mean that, for example, the launch configuration or the hardware features that we use are optimal for this platform. So specifically, for example, the MapReduce kernel is pretty slow and should be optimized for OneAPI Intel GPU backends. We also should be supporting more vendor libraries, but as I mentioned, the need for C++ API wrappers made this a little slow. And finally, of course, application support is something that needs to be improved or at least validated. So definitely here, try it out if you have a kernel abstraction-based or an array abstraction-based application. Try OneAPI.jl out. The benefit is that many people probably will have an Intel GPU. Well, maybe not the MacBook audience, but at least if you have an Intel CPU in your processor, chances are you might just be able to run OneAPI.jl just like that. And that's it for a short overview of the past year of developments. If there's any questions, now is the time.
Have you tried using OneAPI with like Aurora? I think it's Aurora, the big Intel supercomputer that has the Xe GPUs.
Yeah, that's the reason we developed it, but I don't have access to it yet. I heard it's delayed again, so I'm not sure. People here will probably know better what the status of that is.
Are there any plans to support CPUs with OneAPI?
Yes, as soon as OneAPI itself decently supports many more backends, we will definitely consider opening up OneAPI.jl and trying to make it more than just an Intel GPU package, but more of a broadly supported accelerator programming platform. The problem there is that, as I understand it, Intel itself doesn't exactly know yet how to move forward best on this regard. And for example, there's no proposals to introduce a new runtime library that would require us to re-engineer a significant part of OneAPI.jl. So I'm holding the boat off a little bit to see how things change in the next year. But we'll definitely consider supporting more platforms and different platforms as we go.
Can you hear me? So I have a question about like how kernel abstractions and GPU arrays.jl interfaces with OneAPI, because right now, like with CUDA.jl has like the best support for like all the library stuff, like cuSparse, QF50, everything is ported. It's actually getting regularly maintained, whereas in AMD GPU.jl is lagging a little bit behind. Right now, like no rocksparse support, like you have RockF50 support. But like from looking at the code, I understand like there's a lot of overlap between the code bases, like for like sparse and stuff. Like I was wondering, like if like with addition of like OneAPI and Metal, is there going to be like any effort to kind of abstract a lot of that away in like kernel abstractions and GPU arrays and like make the development a little bit more simpler across GPU stacks? Or
good question. The problem is that currently the scope of GPU arrays, at least, is to support whatever we can do natively. So as soon as we have to go to vendor libraries like cuSparse or rocksparse or whatever the Intel equivalent is, it's fairly hard to figure out the exact level of abstractions, what we can put into GPU arrays and what we should abstract away. So there used to be a time that GPU arrays assumed that you had a GPU BLAS library and it had a bunch of functionality calling out to BLAS, and then you had to slot in a vendor BLAS library. The problem is that cuBLAS is not BLAS. It has its own APIs that slightly differ from, and the effort required to go and figure out within GPU arrays what the necessary changes are to the abstractions to support all of these slight varieties across vendors is hard for the development team that we currently have. So that's why all of the vendor-specific stuff is handled in the libraries itself. So cuSparse lives in CUDA.jl. rocksparse will always live in AMD GPU.jl. And GPU arrays is only the stuff that we can do natively. Of course, at some point, and we've started some effort for that in CUDA.jl, we'll start having native sparse array support. We, for example, now have a native cuSparse device array support with broadcast implemented on top of it. If that functionality grows, that we can always move to GPU race because we can compile that for all of the other platforms. But API calls to a specific BLAS-like library, difficult to generalize.
All right. Next speaker is Julian Samaru. He has done like most of the work for AMD GPU.jl. The reason why you have today in basically record time AMD GPU support in Julia. He is a research software engineer at MIT's Julia Lab.
Thank you very much. All right. Let's see if this works. There we go. Is that readable for everybody? All right. So, thank you for that introduction. I will not today be talking about AMD GPU. Taking a little break from my regular schedule to talk about Dagger.jl. This is the other part of my work here at MIT's Julia Lab. So yeah, what is Dagger? So Dagger from a high level is a Julia library really focused on parallel computing. And not just one form of parallel computing. So I'm talking about multi-threading, I'm talking about distributed computing, I'm talking about GPU programming, I'm talking about parallel storage I/O and things like that. Really, whatever hardware you have, Dagger wants to target that and make it easy for you to use that hardware effectively from Julia. So I picked up Dagger.jl maintainership a few years back. It was originally developed by Julia Hub, previously Julia Computing, and ever since I picked it up, I've really been focused on the ability to really be able to write code once and run it at any scale. So I've got a laptop, I want to be able to write code on my laptop where it's convenient and easily just push it to a supercomputer or a cluster or whatever and let it make use of whatever hardware is there most effectively without having to go and change a bunch of code and learn a bunch of different things. So there are some problems in our ecosystem, and maybe I'll hide the Dagger solutions. So there's some problems in our ecosystems that Dagger does solve. For example, if you've ever tried to use distributed computing for a problem, and then you're like, I want to add multi-threading, and then you want to add GPU support, or even some portion of that, you find that it's kind of hard to actually do that effectively. To say, I have a bunch of work and I want to run it across all of these modalities. It's difficult to do that because our libraries weren't built for that in the first place. And so they don't exactly compose. Kind of a corollary to this is that, or really one of the immediate results of this is that you can't spawn a task with some work and have it run anywhere, not with built-in Julia standard libraries. You can't just say, here's a task that's going to do some work, and I don't care if it's going to run on a local thread or a thread somewhere else on another worker in my cluster. You can't really do that with the built-in Julia tools available. There's also this problem that, as we've seen from Tim's talk, that we have more and more hardware that is available of different kinds from different vendors, which kind of all follow the same idea, but they're all different implementations. They all have their own drivers, they all have their own compilers, and we also have different interfaces that we want to work with. Some people want to work with tables, some people want to work with arrays, some people want to just do stuff directly with tasks, kernels, et cetera, et cetera. And so we have this problem of mapping all of these abstractions to all of these backends through a unified system which gives you still all of the same features that you want. And of course, users have all sorts of crazy configurations, and we want to try to support all of them. It shouldn't matter, whatever hardware the user has, we want to try to support that as best as possible. Often users don't really have a choice in that. So Dagger's solution to all of these problems, multiple pieces. So for one thing, Dagger has a unified task concept. So dagger.atSpawn constructs a task, and I'll show some code in a little bit, but basically it has a unified task that can run anywhere. It can run on the worker that launched that task. It can run on another worker, and it will pick a thread. It'll pick whatever Julia thread is available, and it has a built-in scheduler that kind of decides, hey, I have all this work. Let me just kind of throw it out all over the cluster and just utilize our resources really efficiently. Don't mind the machine learning part of the heterogeneous scheduler. That's kind of just a thing that's still work in progress, but we do some reasonably smart things with scheduling. We don't, send a bunch of data around, wasting a bunch of time, transferring data for no good reason. That's really what that means. So we also have high-level APIs for, as I said, tables, arrays, stuff like that. They all use the same underlying support from Dagger. There's no special thing for tables or special thing for arrays. It's all the same low-level API that Dagger exposes to these abstractions, and it all just works fine. And because you have the right primitives that you need to really build all of these abstractions. So we also have hardware awareness. So you load Dagger, and then you load CUDA.jl or oneAPI.jl or what have you, and Dagger detects that, oh, now there's GPUs. Okay, I'll be able to use these, no problem. You don't have to do a lot of work for that. So let's take a look at one of the main interfaces that probably the people here are familiar with, which is distributed arrays. So Dagger has a built-in distributed array implementation called the D-array, and it kind of works like you'd expect. In Julia, this is how you can allocate a random array, 64 by 64, and in Dagger, you can call distribute with that array to split it into blocks of 16 by 16. So we'll take this array that's, you already have allocated, and you can split into partitions, and Dagger is going to spread that across your workers in your cluster or across your threads, whatever makes sense. You can go ahead and do operations like a map on it, and importantly in Dagger, it is an asynchronous, lazy system that runs work in the background. So you launch work, and you can launch more work based on that and keep going and keep going. It's not going to block until you say, okay, now I finally need to materialize a result. Give me back something I can work with, like a Julia array. And so collect is kind of doing that here. But we also use base.fetch for a lot of our APIs to say, here's something that's still maybe computing that we don't yet have. Let's actually get that result. Let's finally materialize that, but lazy by default. So that previous example was distributing an existing array. You can also call a function to just allocate your random arrays directly on your workers. Obviously, that's more efficient if you can do that. So we have APIs for that. You can do rand, ones, zeros, whatever. You just basically add this block specifier as the first argument with your desired partitioning. So things like reductions and broadcasts and all the array stuff that you expect are within the purview of the D-array, and we plan to support all of these. Not everything is fully there, but we're getting there. Broadcast being a big one that does work today. So all of this just works fine, as you'd expect. Go ahead and build up your broadcast expressions, no problem. So yeah, I've been telling you that it's distributed. I've been telling you it's multi-threaded. Let's prove that. I'm not going to run the code today because we know how live demos go. But we can see, okay, let's map over an array and let's return the worker that we're actually running on. And here we can see that, and it's, kind of running off the side of the page, but we can see, yes, we were running our blocks of our greater virtual array, our D array, are executing on different workers. And as I said, we can prove that we're using multi-threading as well. We do the same approach, just return the thread ID, and we see, yeah, we're running across all different threads. And that's across all of the workers. If worker 2, worker 3 has some number of threads, we're aware of that. We use them. So one really cool thing about the D-Array that I wanted to highlight today, we have an amazing Google Summer of Code student, Felipe Tome, that we've been working with. And he has been doing amazing things with taking Dagger's D-Array, revitalizing it, and adding MPI support. So I'm not going to run this demo. Obviously, in a Jupyter kernel, that doesn't exactly work. But you can load the soon-to-be-merged Dagger MPI package and basically go ahead and use a very similar syntax to what you just saw to allocate arrays, but across MPI ranks. And then do the same operations on them. You don't have to worry now that you're using MPI. It's happening seamlessly in the background. The Dagger D-Array is doing the MPI operations for you. And this is nice. People don't usually like to have to write MPI code if possible. And again, yeah, you can see all the regular operations will work. How am I on time? Okay. I'm going to just run through real quick. We have distributed table support. If you saw my talk this morning, you've already seen some of this. Just like the D-Array, we split things into partitions. It allows us to distribute and do a lot of parallel processing. Let's just run through this. We're also here just showing, yes, we're using distributed computing and multi-threading. The key thing here that I said before, there's a single low-level primitive system that Dagger provides, a set of tasks and data primitives. This is what everything is built on. You can build new abstractions on top of this. Just use that same API, you get all the same features. And you have an awesome scheduler, which is aware of GPUs and all that, which is great. Some of this stuff is still in progress, but we do have distributed loops and transducers integrating with the Folds ecosystem. I've been working on trying to get all of this together. Work in progress, and then something recently is that I've been working on is better GPU kernel support. So you want to be able to integrate with kernel abstractions and do distributed GPU kernel programming. I've just got a taste of what you can do here. Of course, all of this is going to be online, so you can try this out yourself. But suffice to say, we try to support all of the GPU backends we can. We need one API support, but that's on the to-do list. We provide all the primitives you need for determining whether you want your kernels executing sequentially or in parallel, and you can really, that's kind of what these examples here are showing, but you can check out the notebook afterwards to kind of see how all of this works. And yeah, that's basically it. Yeah. In summary, use Dagger and let me know if there's anything that's missing any abstractions or any backend support, and we can make that happen. Thank you very much.
We have time for 1 or 2 quick questions.
So maybe this is a general question. So in several talks, you always see, oh, use MPI-JL. Now, in principle, we have a concept of a compute cluster in Julia, and we have the cluster manager, and we have an MPI backend. But obviously, people use MPI-JL directly for a reason, I guess. But is there a path forward to where we can really just rely on Julia's integrated sense of what a compute cluster is, and automatically choose the right communication path instead of saying, oh, now I need to do Julia clustering, now I need to do MPI-JL directly, and so on.
That's a great question. That is exactly what I'm trying to target with Dagger, and that's what I'm trying to prototype right now with the D-Array is for now, you change one little thing, and you automatically get the benefits of whatever cluster system you're using. In the future, it should be possible to even remove that part, so you don't have to specify that. Just let some code automatically detect, hey, I'm under MPI, let me use MPI. So hopefully that answers your question.
In general, why is the Julia cluster system with the MPI backend good enough?
That's a complicated... Potentially, there are many complications there. We should probably take that offline.
Yeah.
So I just want to add, there's an SE workshop called Alternative to MPI plus X. I don't know if they'll succeed, but the conversation's there.
Let's thank Julian again.
Yeah.
All right, this brings us to our final speaker. It is Johannes Blaschke. He's the one pushing Julia forward at NERSC. He's a performance specialist, application and performance specialist.
Oh, thank you very much. Sorry, I get a bit closer to the mic. How's this? All right, so I love the question about why don't we just use MPI, because this part of the talk is going to be about like making people who don't want to touch MPI happy. So this as was previously talked about, Julia comes with an already native distributed computing support, and so I've been working with that at NERSC for a while. So I work in the data science engagement group at NERSC, which is a group that actually focuses on helping users with data-intensive workflows, so not necessarily traditional compute and simulation workflows, but analyzing data from instruments, for example. And so maybe I should also say, what is NERSC? We previously heard about OLCF. That is a leadership computing facility. Their job is to try and get the biggest kind of jobs, the biggest compute available on the planet to work. We are the mission compute facility for the United States Department of Energy Office of Science, and that means we take everyone else. When you are funded by the Department of Energy, you can request compute hours, and this is a decision that's not made by us, but by our program managers, and they will send you to NERSC. So that means that the workflows that are running on our systems, they are cross-cutting across pretty much all of the scientific domains. We have about 9,000 active users. They are distributed across about 1,000 projects. And these users are globally distributed as well. What I really like to point out here, though, is most of our users, about 59%, are from academic institutions. So we are not solely a government agency. We cater mostly to academics. And the thing that I really like is this part down here. If you add up postdocs, grad students, and undergraduate students, you get more than 50%. So most of our users are actually early career scientists. This might be a reflection of the fact that most of the work is done by the postdoc and not by the professor. But it also means that it's a very young user group. All right, so if you were to pop open a cabinet of so we currently have one production supercomputer. Cori, which was our outgoing machine, has been decommissioned. In case you were still a Cori user, you've lost your data on Scratch. So we are running Perlmutter now. So if you popped open one of those cabinets, what you would see is a fairly sophisticated chassis to manage power and cooling. But essentially what you care about is we have two kinds of nodes, a CPU node and a GPU node. If a GPU node has 4 A100, so NVIDIA A100 GPUs, and one AMD Milan CPU. Crucially, it has 4 NICs, or network interconnect controllers, interface controllers, sorry. This will be important later in this talk. Whereas a CPU node has 2 AMD Milan CPUs, but only 1 NIC. So just to summarize what I was just talking about, most of our users at NERSC are non-HPC experts. So, and it's important, we can't force them to become HPC experts. We can't say, well, if you don't learn HPC, you can't use our systems. and additionally, the workflows that are running on our systems are incredibly varied. So we have to provide a wide range of capabilities, and that's already reflected by the fact that we have 2 different nodes, right? And so the challenge for a package like distributed is that it needs to, essentially it needs to, out of the box, know the right thing to do. So this is something that I've been thinking of for a while. It's actually something that Valentin, like a thought that Valentin initiated. So Valentin, you get credit if this is terrible. No, I hope it's not terrible. No, the idea is we need to rethink about how distributed actually talks to the resources that it needs to use. And so I want to start with a workflow support story. A while ago, about a year ago, I got a ticket that said, you know, Perlmutter is about 100 times slower than our university cluster. And of course, you're like, oh boy, what the hell's going on there? And so the user then produced this small minimal reproducer, and it actually represents what you see a lot in terms of these non-MPI HPC workflows. It's some sort of, here, this is not Dagger. I told them later to use Dagger, by the way. But so you have some, you configure some cluster manager, and here what you actually do is you use srun to start a pool of workers. You wait for the workers to start, and then once they've all started, you run this little benchmark that essentially just is intended to stress test the communication by copying this random data for several iterations, in this case 20 iterations. The reason why you might care about this is because imagine you have a sophisticated workflow that's making decisions and you want to start additional workers, right? So you should be using Dagger, but at the time, you know, the user was using this. And by the way, Dagger uses distributed under the hood, so all of this is still relevant. And so what we found is, just by thinking about how much data we're transferring, we were way too slow, and the scaling was horrible. So ignore the red blocks here. The blue blocks are sort of by what happens by default. So as you scale from 2 to 20 workers distributed over 2 nodes, your time in the loop is just becoming, this is the per loop iteration time, by the way. So it's a problem. So we started digging around, and we found the problem. The problem is, and the way I found the problem, by the way, was that the admin sent me a Slack message saying, you're spamming the node management network. It's destabilizing the cluster. Stop it, please. And that's really what ended up happening. Our management network interface is the lowest number network interface on the nodes, and Socket by default just grabs that. So we were dumping all of our data across really normal Ethernet. And so after discussing with the admin, they said, well, it's easy. The fix is easy. Just put this in your startup.jl and tell every user to do that. Now, this actually doesn't solve the problem, I think. And there's 2 reasons. The first one is users don't read documentation. So even if you put this up in big red warnings, people will, even if they're good intentioned, will miss this. And so the effect that I like to show is, so you have a lot of good intentioned users, and they're all trying to get onto this log here. And they all want the system to be stable, but it's actually oh, okay. The Wi-Fi isn't good enough, but basically these turtles are destabilizing the log. Eventually they all fall down. Anyway, so oops. So the other reason what this doesn't fix is if you look at one of our GPU nodes, you see you have these 4 NICs here, and that snippet there essentially just picks H's and 0. So it picks this NIC over here and ignores the rest. And you can't actually just say, oh, well, then I'll create a more sophisticated script. Well, it gets very sophisticated because we have different kinds of nodes and they have different configurations, right? So you then have to start looking up host names and things like that. That's kind of nasty. So instead, this is what we were working on. The first step is, well, we've got hwlock. How about just using that to tell me which NIC is closest? Sounded like a simple idea. Turns out that it required quite a lot of additions to HWLock to get the PCI interfaces to work properly. But that works now, so yay. And then use the distance on the HWLock tree to find out which NIC is closest to what core. And then, so this is effectively done. This is edge cases are still a problem, but that's okay. And here is a conversation we still have to have. How do we integrate that with distributed.jl? And just to demonstrate how it works, if you use HWLock and just print the tree for a GPU node, this is highly truncated. It's like 10 pages long. There's USB ports. I didn't know, but I saw USB ports. Anyway, the point is, though, you have, when you truncate out all the stuff that you don't need, you see a NUMA node, and then you will see a host bridge and PCI bridges, either to the HSN or the management network, and you can see the different HSN interfaces here. And so what we want to do is we want to map these to different processes, depending on where the process is running. And so, so this is just showing how it actually works in the library. So basically, for each process, we can compute the distance, and we say, well, we want this one. This is the one we bind to, okay? And this is actually what those red bars are about. So when you then run this with thread binding to cores, it works great. There's no problem anymore. In theory, at least. And so it does still, there's a caveat here, though. So the way that this is architected is this package here, which is still a bit experimental, handles the mapping. And then it also, at the moment, handles some machine-specific configuration. And we have to kind of think about how to best support that. And so that brings me to my to-dos. Essentially, this is pre-alpha, but we want to make it alpha and beta very soon. So if you are interested in discussing what, especially this question about how this gets integrated with distributed, please discuss. We can have beer or not beer. And if you also want to try things out, let me know. Yeah, so. Any questions? I answered all the questions. Excellent. Oh.
Thank you. So I guess the question is, I mean, maybe this is, how, do you have any ideas on how it should integrate with distributed? I mean, distributed is a bit of a, it's been around for a long time. Right. There's some funny interfaces in there for anyone who's ever delved into it. Artisanal, that's an extra word. Yeah, do you have any thoughts?
This is my opinion, of course, and I don't want to devalue anyone else's opinion. I think what we are aiming for, what I would want to aim for, is something that works as seamless as possible for the user. So that should be the constraint, and then within that constraint, I would like to minimize the amount of dependencies that this introduces. So one example could be that if HWLock isn't installed, then just don't use it. It sort of creates a little bit of an edge case where it might just be like, so the plan that I currently have, and people are welcome to give feedback on that, is a preferences file that the sysadmin puts in a global path, and if it requires binding to the cores, then it looks, do I have HWLock? Can I run this? If not, here's an error message and force the user to add it. That would be one way. And if it's just on your laptop or so on, you don't really need HWLock. Behind you.
Hey, so I heard a little bit about pinning to cores. So are you planning to have integrations with thread pinning, .jl? I believe that's the name of the package. Or are you planning to do this kind of more just from the low level? How is that going to work?
So basically what if you don't use thread pinning and your processes hop around, then, well, you still get the speed up of having the high-speed network, but then, of course, you don't have the NUMA locality, right? It's always good practice to use thread pinning, at least for the stuff that I do and the stuff that I've seen. So, but it's not going to be a requirement, no.
Yeah, okay. I have another question. Oh, you
Sorry,
don't have
just
time.
1 second before you post your question. Since mapping was mentioned, just one more comment. The question also, there's dependency as well, right? Like I mentioned, I use currently LSCPU as a backend. I could use HWlog, would be fine, just a bit of work, but it's still a dependency, right? So you would, have to know about the system if you want to schedule on a system, right? So, and not everyone is willing to add this. We also have this discussion with Julia Base, by the way, whether we should spawn the number of threads per default according to the core, so CPU threads or whatever. And to figure that out, you have to have a dependency, and not everyone is willing to, have that. Sorry, pose your question.
Okay.
Oh. Yeah. 1 second.
I was taking a look at your GitHub page for HWlog.
Okay.
But like, is it possible to use InfiniBand with this kind of setup?
I don't know.
Because it's cited here, like, it also gathers various system attributes such as cache memory information.
Right. So HWlog does find InfiniBand devices, right? But I thought you were referring to distributed. I don't know if.
So
right.
can I use it distributed?
I don't know if distributed can. It's.
Distributed.jl just uses TCP/IP, and if you want to get anything faster, MPI, or if you're looking for a fun project, reach out to me and we can talk about UCX.
+1 on the UCX part.
Yes. Also, UCX does these adapter selection automatically.
All right, so let's thank Johannes again. And we now have another 15 minutes of like Q&A discussion that Carsten will moderate, and he will start by reminding you of the BOF that will happen.
And the survey, actually.
And the survey.
So first of all, I don't want to stop the discussion because I think it's going in the right direction, right? We can just continue there. We also don't have to fill this up, right? There's a BOF tomorrow, but I thought I wanted to end on the discussion and not just a talk. But as was mentioned, here's the survey again. If you didn't attend earlier today, we are trying to conduct the Julia HPC survey regularly. We've done this last year at JuliaCon. We've done this at Supercomputing at the BOF. Now we're doing it here again. I will mention it in the Julia HPC BOF tomorrow as well. Please fill it out only once during this JuliaCon if possible. And if you haven't done so, that's the link. That's the QR code. And the reason for this is just to get a feeling for our community, right? How large scale we do HPC, which systems people are using, and so please go ahead and do the survey. You can also put your email in there, and we might even share the results if we don't forget about it. We'll try to keep that in mind, and then you'll get the results as well. Yeah, okay, and since you mentioned it, there's also the Birds of Feather session tomorrow at 3 p.m. as a reminder in room 144 downstairs at the first floor. And that will be the major discussion round where we'll have 1 hour to discuss topics. You can suggest topics. We don't have a complete format yet. Like as much input as possible is what we want. And yeah, and right now, if there's an opening question, like I would have posed the opening question inspired by the questions that was just asked. How optimistic, because some of us at least agree that distributed is a nice interface, right? That is convenient. You can, not just because it also do it in the Jupyter Notebook. Some also claim, I know Johannes, the last speaker, also has that opinion a little bit, that this master worker flow is sometimes more natural than, this MPI, everyone does the same, The question that I would throw out for the next 10 minutes is how optimistic are we that distributed can become competitive to MPI, also performance, right? Not convenience is one thing, based on UCX, for example, and in what scale are we targeting, right? Are we just saying, you know, we make the regular user happy, like that uses a bunch of parallelism, right? A few cores, or how high are we aiming, right? Are we really aiming to be competitive at 1,000 nodes, or a few thousand, or like 60,000 nodes? Yeah, comments in that direction, and please feel free to add points. And
I'm going to jump into that. So from a historical perspective, one thing that has always held distributed.gl back is that it is part of Julia as a standard library. And so it hasn't been able to evolve independently of Julia as we go along. And despite some of us being maintainers of Julia, it is not the most encouraging thing when you know that your features or bug fixes will happen 6 months, 9 months down the road. And it really doesn't give you this agile feeling that you get from the rest of the Julia ecosystem, where I can push out a patch release and break everybody's code in a matter of minutes. So distributed.gl, I think, can be as performant as MPI. It's kind of funny. I tried really hard to prove that distributed.gl is slow. I failed. Spent about 3 months on that. Because actually it turns out if you are doing serialization because you're dealing with arbitrary data types, doing the serialization and using then TCP/IP for packages to send over the wire is actually rather efficient. So I think distributed.gl can get to a point where it's performant and has all of the features and gets there, but it first must leave Julia and not be a standard library, or be a standard library but be independently developable outside Julia.
Yeah, in that spirit, I also want to say that especially when new systems are being brought up, the vendors will change their backend. They will change. Things are fast moving. So at least having the backend, if you want to take this approach of like an interface and a backend, then the backend needs to be agile.
I guess that connects a bit to my earlier question, and maybe I'm not the only one. So my understanding was that if I use MPI cluster managers, and if MPI-GL is configured to use the vendor libraries, and if I'm a little bit lucky, that then actually the messages will be sent over the low latency network. So would that be comparable? I guess you're also targeting scenarios where you actually don't use MPI at all but get similar performance. But if I were to go the MPI cluster manager route, is that viable, or are there just other things that just make it still slower then?
I can pitch perhaps into that one. So there's two things. So one is the serialization. So at the moment when we send stuff over through distributed, everything gets serialized. Whereas MPI typically, your classic MPI job is sending Fortran arrays in Fortran that are fixed size, everyone knows, and that's what MPI is built around. Is like I know exactly what I'm sending. So if you send stuff via like serialized MPI, it has to first send, okay, I'm sending this much data, allocate some stuff, and do that. So you have that already issue of like A, serialization, and B, memory allocation. Then you have the second order effects of if you're allocating memory, then you're also going to be GCing more than you would otherwise, and that will typically cause my experience, like Hello Exchange, which is like the bread and butter of that you don't want to be GCing very often because that just kills your scaling.
I think I would just use remote channels basically between and then send arrays.
Well, yeah, we still has to estimate what data.
Yeah, so, I mean, there's one problem which is basically MPI. The way MPI works is you send messages of a fixed size. So you serialize everything at once, and then you have a gigantic buffer, and you send that over the wire, and you have to wait first for the serialization to be done, and then you start the sending instead of being able to interleave that. And the other side is sitting there spinning, doing an MPI probe every cycle, and is then, oh, now I get a message, and now I need to decode what the message is, and I need to do a lot of extra work to emulate the same features that TCP/IP has. So in some ways, that is why like the MPI cluster manager is actually not faster, despite using the faster network.
Going back to historical perspective, Valentin bro, there's attempts in the past, HPCS, right? PGAS was the whole thing, partitional global address spaces. So it's have been tried in the past, but for those who don't remember or didn't live that time, Google X10 or Fortress or Chapel, right? That was the lesson learned.
So one thing I wanted to kind of say about, seeing if distributed can kind of take the place of MPI for many use cases is that it's not just about taking what distributed is today and incrementally improving it, and not to disparage what you're doing. I just mean that we need more than that. We need really, and this is from my perspective as Dagger.il's maintainer, is that you still need to have other abstractions that allow users to be productive. So, distributed, I've seen so much distributed user code where users are doing remote calls and they're creating some global variables and stuff on each worker, and then they're going and trying to get all the scoping right for that, and then trying to manage data movement and where data is and data transfers and stuff, and it's very painful. They shouldn't have to deal with that. And for most users, they really just want to say, here's my data, here's my computation, combine the two, and be able to hand that over to something which is then able to handle the rest of the details, doing the data movement in the background, because of course you don't want to be waiting on data movement. And putting work onto threads if you have threads in each of your MPI ranks. So really my point is that there's still more work to do, but I don't think it has to be in distributed. I think we just need the interfaces from distributed to allow that. And I think we have most of that today.
What's the, is there a path, or do we have this already when it comes to hierarchical scheduling? So, for example, I do this Bayesian analysis package. So, like I said, I have my Bayesian inference engine that needs to start 8 MCMC chains. But then the user will provide some physics model that runs on these 8 chains and might also want to do multi-node, multi-threaded computing. So I need to schedule something on groups of nodes, and then the user is supposed to use all those. So how do I express that, or how will I be able to express that without them fighting over each other?
Do you want me to? I mean, again, that comes down to what primitives do we have to enable that? What primitives do we have that we can give to users to be like, yes, you can, pick an arbitrary number of cluster resources and say, okay, I'm going to put something in there that's going to use something in there. Yeah, and I agree. You need an abstraction for that. I don't know if it needs to live in distributed though. And I mean with the somewhere. Yeah, right.
Maybe one comment from my side. The question there also is the trade-off between convenience and performance, because the point is this tool that we are imagining or describing, right? May it be a Dagger or something else, right? Like a scheduler of some kind that does the magical part. It will inevitably be, or most likely, be slower, at least intermediately. In the for the next couple, also Dagger, right? I know that you have benchmarks that are good, right? I would assume that there are also lots of benchmark where Dagger has subpar performance, right, compared to manual implementation, and that's fair enough, right? I mean, you have to start somewhere, but the question is this acceptable, right, for user X, right? How many people here, like the climber or whatever, right? Is it acceptable to say, I use this tool because it's convenient, right? Maybe even much more convenient than MPI. However, there's a performance hit X, right, which I cannot accept for the next year or the next 2 years, and most likely it's not even a definite number, right, for for the years. So that's a question that I often have in mind, right? Like, how willing are we to, wait on these things? And my feeling is that maybe the community is slightly split. There's the, one kind of user who doesn't want to become an HPC person and just wants an easy tool and uses whatever's out there. And then there's the other folks who run computations where performance literally matters, right? Everything, like the tricksy folks, right? They would never use distributed or Dagger or whatever unless it's within, 10% or whatever of MPI, right? That's just reality, and that split has to be addressed, I think. Last comment?
But in that sense, it's not just what's acceptable to the user, right? It's also what's acceptable to the compute side. Yeah. Because if they say, oh, but you can't load out our machine more than 50%, we're not letting you on the machine, at least not above 5–10%, then the user can say whatever they want about I'm willing to wait because they're not going to schedule him, right?
Johannes, if you want to comment, one sentence or two, and that's the end of it. So
I would want to encourage people to think of it as a spectrum, not a either or.
Yeah. All right. Thank you guys for attending, for the discussion, for everything. I hope you had fun today. Tomorrow, as I said, birds of feather. Hope to see you there again for lots of more discussion, and enjoy the rest of the day.
unique in astronomy in the sense that every aspect of the pipeline really depends on computers. Sometimes even forming the telescope is done in software. So this is pretty interesting, and it kind of allows Julia to lead the forefront or maybe do the whole stack. So from telescope forming to calibration and imaging. And we're going to have a wide variety of talks, and we're going to get started from a local person, Sarah Soon, who is a member of the Event Horizon Telescope, is going to review a little bit about how we actually make black holes. So, all right.
All right, thanks, Paul. So, as Paul said, I'm not a Julia person. Paul is your guy if you have Julia EHT questions, and he'll be talking about it in the second half of the session. But I wanted to just kind of give a broad overview about why we're interested in Julia and tell you a little bit about the story of the EHT and where Julia actually fits in that aspect. So first, why are we interested in studying black holes? This is what we do as part of the Event Horizon Telescope. Well, the kinds of black holes we're interested in are really supermassive black holes. They reside at the centers of most galaxies, including our own. And these black holes, they power these huge jets of plasma that you can see here on these beautiful photos. And these jets are, this process of launching these jets is the most energetic process in our entire universe. And we don't quite understand how these happen. And these jets have a fundamental role in where we come from because they play a vital part in how galaxies form, how stars form, and this whole feedback loop of radiation into the host galaxies and nearby galaxies are a major part of the evolution of the universe. So understanding black hole fundamentally helps us answer one of the most fundamental questions of humanity: where do we come from? So there are about 3 open questions in the field of black hole research right now, these broad-ranging ones. So what do black holes teach us about space-time and fundamental physics? Black holes are the simplest signatures of gravity and space-time, so they can teach us a whole lot about theories of gravity, how do black holes feed and launch these jets that I talked about, and how do black holes form, evolve, and affect their environments. Now, EHT is not so much of a galaxy evolution instrument. We really try to peer down to see black holes as they are, and so we're mostly interested in the first 2 questions. So there are 2 black holes. The 2 biggest black holes on the sky are these 2, the M87 black hole and Sagittarius A star. M87 lives at the center of the M87 galaxy. It's 55 million light years away from us. That's really far. But it's also 6.5 billion solar masses, which means it's a huge black hole. It's actually one of the most massive black holes in our local universe. And because of its mass, its size on the sky, which is proportional to the black hole mass, is actually about 40 microarcseconds, which is about the size of a donut on the surface of the moon seen from Earth. That's pretty small. Sagittarius A star, on the other hand, is much smaller as a black hole. It's only 4 million solar masses, but it's 27,000 light years away from us. It's in the center of our own Milky Way galaxy. Now, Sagittarius A star is about 50 microarcseconds on the sky, so a little bit of a bigger donut, like a Boston cream, on the surface of the moon. So we have these 2 black holes, and they're about the same size on the sky, but 50 microarcseconds is really, really tiny. So how do we get a telescope that can make an image of it? Well, it turns out if you make the calculation and you observe at a wavelength of about 1.3 millimeters in the radio band, where you can peer through all the gas between us and the centers of these galaxies, the size of the telescope you need, the diameter, is about 13 million meters. Now that's a big telescope, and it turns out funding agencies can really pay for it. So we decided, okay, let's find another kind of hack in order to make a telescope this size without actually building one this size, like a Death Star telescope kind of thing. So what we did is use this technique, which won the Nobel Prize in 1974, called very long baseline interferometry. Essentially, we connect telescopes by simultaneously observing the source and computationally design a telescope, a virtual telescope the size of the Earth, through the connections between these telescopes. Now, these telescopes are not physically connected. These are just kind of invisible lines around the world, but they're connected via our instrumentation. So a brief recap of how very long baseline interferometry works. Now, if you're into radio imaging, most of the imaging techniques and data you've probably dealt with is connected element interferometers. So things like the VLA or ALMA, or these bigger arrays that are coming like LOFAR, like DSA 2000, like the SKA. But we're dealing with a very different regime with the EHT because our telescopes are not connected and there's really very few of them. So very long baseline interferometry uses a pretty simple concept, but I'll explain a little bit of the challenges. So we need to observe the signal from the source from the black hole at the exact same time at each telescope in order to combine the signals from all the telescopes and make an image. And so the source emits waves, and because it's far away, the waves arrive as plane waves on Earth. Because our telescopes are pretty far apart, it turns out that there's a time delay that we have to take into account. So you'll see if you follow one of these lines that one of the waves will arrive at the lower telescope earlier than at the other telescope. If you don't take into account this distance, this time difference, you destroy your signal. And so how do we take into account this issue? We actually use very precise atomic clocks at our telescopes, which are these hydrogen maser-powered clocks. They're so precise that they lose about a second every million years. And so these clocks time tag our signal, and we digitize it, and we record it onto standard helium-filled drives. And so essentially, we freeze the light that arrives at each telescope into these hard drives, and then we combine them at a later time where we can make all these alignments. So building the EHT was a pretty long process, and it was started in the early 2000s with these 3 telescopes here. I need to, Paul, I'm sorry, your Netflix suggestions need to be removed. All right, so it was started in 2007, and then over the years, we've added more and more telescopes, and we've also lost some that got decommissioned over time. Then we arrived to 2017, where we had 6 different locations, 6 single-dish telescopes, and 2 phased arrays, these 2 here. Now, you'll notice that all these telescopes look completely different from each other. This is because we did not build them as part of the EHT. We tried to borrow them and make collaborations between these facilities that were built for completely different science in order to join our endeavor to make an image of a black hole. Why these telescopes? Well, they just happen to be able to observe at 1.3 millimeter wavelengths, which is not an easy feat for radio observing. They are at very high and dry places because water vapor and instability in the atmosphere completely destroys our signal at this observing wavelength. And so these telescopes came together, we installed these clocks and these receiver systems, and we carried out our observations. So then how do we get from recording to image? So we record our signal onto our hard drives, we ship them to what we call a correlator, which is a special purpose supercomputer at 2 different locations that combines the signals. So what it does is that it plays back these frozen light from the telescopes, and it realigns them. It fixes this delay, time delays due to the Earth's curvature, different properties of the Earth's model, location of the telescopes, and atmosphere. So it corrects for all that. And then it extracts the signal from the black hole that is correlated between the pairs of telescopes. Then we move to the calibration stage where we do finer corrections of the atmospheric effects in the data, more instrumental effects, so that we can average down the data over time and build up our signal to noise. Then the final data, which is deemed analysis quality, then moves on to our imaging techniques that try to look for a sky image that fits the data very well. But we have a problem, because what we deal with VLBI is what we call an ill-posed imaging problem. We have an infinite amount of images that could potentially fit the data. The reason for that is because we are sampling a very sparse part of our Fourier space. So we observe, what we measure at the telescopes is complex visibilities. We have a phase and an amplitude, and we look at everything in the Fourier domain and then transfer it to an image domain to make an image. So we use this technique called aperture synthesis, where the Earth's rotation helps us fill our coverage. That is why we have more points here than we really should have if we just take a snapshot with just our few telescopes. And then we combine the data on temporal and spatial scales as we sample over our Fourier space as the Earth rotates, and the lengths between, the relative lengths between our telescopes actually changes in projection to the source. So that's how we stack all the data, and then we make an image. But making an image was actually a pretty difficult process because we were obviously biased about what we could imagine a black hole to look like because of our simulations, theory, et cetera. So we tried to find a way to get rid of some human biases by doing this blind imaging stage. So we split our imaging group into independent teams, 4 of them for M87, 5 for Sagittarius A star, and then each team had to image independently using whatever software they wanted and whatever user-based choices they wanted within that software. Then after blind comparisons of the results, we opened up the data and then we moved on to the second stage after we agreed across teams. And the second stage was a very extensive parameter survey with our imaging pipelines. And this parameter survey involved the creation of synthetic models that would mimic our data but have different ground truth images. And so we did a kind of simulation-based inference or kind of very primitive machine learning type testing on our synthetic data. And we tested thousands and thousands of parameters of our imaging softwares and then ranked them by how well they were able to reconstruct all our synthetic models. And then the top ranking ones were used for the black hole data, the real EHT data. Then we moved to a third step, which is image validation, which is how well they fit to the data, how consistent they are to the other sources we observe in the same observing campaign, and how robust the structure is that we're seeing to individual choices, like if we kick out a station in the array, what happens to the image? Can we trust this structure? So this really worked great for M87. And for M87, in the imaging, we used 3 imaging software packages. One was an inverse modeling technique, which is clean, which I'm sure you've heard of if you do radio imaging. It is the traditional radio imaging method. And then we had 2 regularized maximum likelihood methods, which are forward modeling techniques, which were designed specifically for the EHT and for solving this sparse sampling problem. So we tested thousands of parameters, and then we ranked them, and then the top ranking ones for each of these 3 softwares were averaged together to make 1 image per observing day of the EHT. Here are the 4 images. We also have a big modeling suite that modeled the ring for M87 and measured the mass of the black hole to be 6.5 billion solar masses. We also did the sim thing for polarization, where we used 5 individual softwares, the 3 imaging ones and 2 more posterior exploration MCMC softwares to look at polarization, and we reconstructed the spiral structure here. The spiral polarization structure tells us about magnetic fields near the black hole. And magnetic fields, these magnetic fields tell us that the magnetic fields in M87 are pretty ordered, and they're pretty moderate, which means they're able to launch this jet that we see in M87. Now, these 2 black holes, as I mentioned, they're pretty different in size. And so just to give a kind of sense of scale between the difference, here's M87. The entire shadow engulfs our solar system, including where Voyager 1 currently is. Sagittarius A star, in comparison, could fit inside the entire orbit of Mercury. Now, for M87, because it is so large and light has a finite speed, it takes a few days for light to go around the black hole. This means that in our aperture synthesis method, where we stack data over time, our image is virtually static on the sky. And so we can do this aperture synthesis and make a static image. For Sagittarius A star, because of the size difference, it takes light only a few minutes to go around. And so every few minutes, your image is structurally changing, which means aperture synthesis actually breaks down. If you try to make an average image over 8 hours, you have to deal with what we nicely call at least motion blur. The variability of the source is pretty extreme, and it makes making an average image very challenging. For Sagittarius A star, we use 4 independent methods, the same ones for M87, plus an additional Bayesian imaging method called Themis. Now, the problem for Sagittarius A star is that we did this whole parameter survey, where as M87 ranking the parameters were pretty easy, and we had top ranks. For Sagittarius A star, there were thousands of parameter combinations that fit the data the same. And so we were in a little bit of a pickle. How do we make 1 image from this? So what we did is use a clustering algorithm. So I want to show you a little bit what it does. So here's a movie of the Dolomites. One's a pretty variable movie, one's a pretty static movie. We take our camera and we make different long exposure images of these 2 movies with different camera settings. And now we're going to cluster them into 4 independent clusters. This is what we did for Sagi star. So if we do this with these clusters, the very variable one has 3 clusters where you see the Dolomites and 1 cluster where you don't see it because of all the clouds that pass through. I'll let it replay one more time. So then when you do this, you'll notice that the 3 ones that do show the Dolomites, they have pretty different kind of cloud coverage. And then the one where you don't show it is really where the clouds are all covering it. So here are all your long exposure images, and then the ones for the pretty static movie, and then you make the clusters 1, 2, and 3 where you see the Dolomites with different clouds, and then 1 where you don't see the Dolomites. And then for the pretty static ones, they look virtually the same. Now this is what we did for M87 and Sagittarius Star. So for Sagittarius Star, we had thousands of images that fit really well, and we clustered them into 4 clusters. And then we ended up with different 4 clusters for Sagittarius Star, 1, 2, 3 rings with different structure along the ring, and then 1 non-ring cluster. The non-ring cluster for Sagittarius Star is only about 2% of the entire set, so we're pretty confident that it is a ring, but we're not as confident as for M87 about the brightness distribution on it. So this is where the story ends for EHT for what we have published so far for these 2 sources, but we've observed a lot more since then. We have observing campaigns where we've added more telescopes. But right now, the EHT has only 11 telescopes, so we haven't solved our major problem of really undersampling the coverage. So where we're going next is really what I want to show you a little bit of, and then Paul will talk about more. What's next for us is what we call the next generation EHT. So this is what the EHT looks like right now in 2023. What our plan is to really increase our coverage. So right now we're using every telescope out there that's available for us to use at 1 millimeter. What we want to do is build new telescopes and put them at perfectly chosen sites such that our coverage is enhanced when we make images. So we have a 2-phased approach where we have 5 new stations by phase 1 and then up to 10 new stations by phase 2. Now, if you have this nice simulation of M87 here with its jet, in 2017, we don't see the jet because we have all these gaps in our coverage. And with the NGHT, we really expect to make these kinds of images on a regular basis, and we want to do monthly monitoring of the source to make a movie. And then you'll see this connection between the ring and the jet. Now, making monthly images, monthly observations is a whole lot of data, and we can't just carry out making these enormous parameter surveys across softwares every time we want to make an image. And so we had to think about how to systematically change the way we build software in order to make proper systematic analysis of the image space. And so one of the major aspects of that has been our move to Julia, and Paul will talk about it with his amazing code comrade and what that has been able to do for EHT and for NGHT type observations. Now I just want to end, I don't know if the audio is going to work though. We haven't tested it, but we have like
April 2019, the Event Horizon Telescope saw the supermassive black hole that launches a jet from the center of galaxy M87. Months later, a sharper image, as if through polarized glasses. Now, May 2022, the hard-to-see black hole at the heart of our own galaxy. What's next? The next generation EHT will allow us to answer a new set of deep questions. How does a black hole power jets like M87's? Can we make a movie of the actual jet launch? And can we sharpen our focus to see fine details of light as it orbits a black hole? To meet these ambitious goals, we are dramatically expanding our Earth-sized telescope. The NGEHT will transform our view of black holes by increasing bandwidth, adding observing frequencies, and establishing new dish sites around the world. By adding dishes to the global array, the NGEHT will allow us to observe the link between M87's spinning black hole and the near light speed outflow as never before. And by observing each week, the NGEHT can make the world's first movie of a black hole. With the NGEHT, we could begin to see the first of the infinite rings orbiting around black holes, allowing us to measure how much black holes are spinning, test Einstein's general theory of relativity, and reveal the nature of space-time itself.
Yeah, this is where I'll stop. Thank you.
All right, so let's get started with questions. We have time for a few, and I'll also ask the next speaker to come up.
Back to the slide of like averaging all the images. Why?
This one?
Like, why isn't it just like a movie of all the
So the pictures you see at the top here, they are actually not snapshots of a time series. They are average images of like 8 hours of looking at the source, but with different parameters of our software. They just happen to all pass through this criteria of these synthetic data tests, and so we can't tell apart which of these ones is better than the other. They all fit the same because the time variability of the source is really what creates all this kind of movement and differences between each of these images. But these are all like these motion blur, long exposure images. Each one is a long exposure image. Yeah.
Any other questions?
I think you have to ask this. Don't we already kind of have a movie of, say, A-Star?
We don't. No.
We do not, no.
We do not.
They have not published anything. I have not seen a movie from them. Yeah.
We have done tests of dynamical imaging or movie making with our data.
I've seen the movie, but maybe then I should.
I see. Well, in our papers, we have done tests in which we try to reconstruct a movie, but we've deemed that the coverage is way too sparse to be able to disentangle any motion from just effects of the gaps that we have in our coverage. And so right now, really going to NGHT, adding up to 10 more stations is really where it's going to make a difference in how the snapshots look like for Sagittarius Star, and really will make the jump into being confident about movie structure and actual motion in time.
Yeah.
So you showed that you get more coverage as the Earth rotates, and could you not use like the orbit of Earth or satellites or things like that to continue to grow coverage outside of? I mean, maybe that's more expensive. I'm just curious.
Oh yeah, we can certainly. So there's currently, I think, one space mission that has been successful in doing this for VLBI, which is called Radio Astron, which uses one satellite dish up in space with a ground array. But that one only goes up to 1.3 centimeters wavelength. So for millimeter timing of the satellite and the position, and also downlink of these massive amounts of data are the challenges that we're facing forward. But we are actively thinking about space missions to increase our diameter, to increase our resolution. And in that way, actually, going up to space, we can make images of up to 10 more black hole shadows that are out there just within the limit of reach with an actual satellite that would increase our resolution. Yeah.
We should move on. Let's thank our speaker again and start the next one.
What are the chances that this works? Survey says, hey.
Okay, so let's get started with our next talk. Here we're going to hear from Kieran Sheila, and here we're going to talk about real-time stream processing for radio interferometers in Julia.
Yeah. So this is going to be a little bit more dry by comparison of some software minutia of this process than the fantastic results presented before. But we're going to talk about... It's still interesting. It's still interesting. So just to introduce myself quickly, like I said, my name is Kieran. I'm a PhD student at Caltech working on two projects, the DSA 2000 telescope and this smaller project called the Global Radio Explorer, GREX. So I'm relatively new to radio astronomy, but I'm getting my hands dirty in the software a little bit, and I've found out some interesting things, and a big Julia user, so I'm trying to see how we're going to incorporate Julia in the process of specifically real-time imaging for upcoming radio telescopes. So if we look quickly at the architecture of specifically an FX architecture radio telescope, we'll have all these antennas, say N antennas, spread around a large area, not quite as big as the EHT, but say with the DSA 2000, a couple square kilometers. And then you have this analog signal path. All the information is digitized. Then that is channelized with a Fourier transform. Big transpose operation, where then you want to have correlations of every frequency channel, and those correlation steps need to receive every antenna. And then you have some science pipeline. So there's a lot of data crunching through this whole thing, and we're going to talk about specifically the last step of this process, which maybe the last two if you include some kind of software correlation, that is, if it were incorporated in the software and not some like ASIC or something specific. So if we're trying to look at how much data that is, we're thinking on order of hundreds of terabits per second at kind of the high end, which is insane when you think about it. We're talking about years worth of internet traffic in a month or so. And so how we actually write software that can do this is exceptionally non-trivial. And the way you parallelize it, like the specifics of how you parallelize it, become really, really important. And you can think that this data comes in chunks of which antenna it is, how many, if you're doing beamforming beams, polarizations, the channel itself. So it's quite complicated. So normally the way we tackle this is some kind of stream processing framework, because after you've digitized it, you want to do something. If it's making an image, there's quite a few steps before you actually make the image, such as removing radio frequency interference. You might want to do some requantization to a different bit depth. If you're doing transient pipelines, such as looking for fast radio bursts or pulsars, you want to do some dedispersion steps. Or if you're doing some time domain stuff like working on cosmic ray science, you want to do maybe FFTs or FIR filters, things like that. So how you do the stream processing, normally you want to parallelize these different operations. So while you're working on, say, if it's an FRB pipeline, you're working on the dedispersion step, you want to be capturing packets on another thread, right? You don't want to do all this at one time because that wouldn't make any sense. But again, like as with anything, there's pesky details for how you actually implement this. And an interesting question, the first interesting question is, how do you deal with back pressure? So you have this, a bunch of operations that are strung together in a pipeline. If one is occasionally slower than the cadence in which you're trying to process information, then it's going to have to pause upstream execution because that's the only thing you can do. So in some circumstances, that's okay, in some it's not. So how do you actually accomplish that? And of course, having some way to observe how, what processes are being slow, et cetera, it really, really helps this. And if you're doing, most radio telescopes have some kind of heterogeneous compute where you're doing some processes on the GPU, some on the CPU, how you move the data, how that moving of data is incorporated into the entire stream processing framework. These are all kind of hard details to solve. So in looking at how to do this with my own telescope, G-Rex, the one I was told, the software package I was told to look at was this thing called PSR data, which has been around for a while. And the way it works is it's a C library that effectively just gives you an API for these ring buffers in shared memory. So you write programs that do a thing, and on the input and the output, you attach to these PSR data buffers, which shuffle data in, shuffle data out. It's operating on bytes. There's nothing really super special or magical about it. How you deal with metadata is a little bit tricky. It's usually just another set of ring buffers that you have to attach to. I have found this software to be rather buggy, and if anyone uses PSR data and wants a little bit less painful experience, I have a REST wrapper called PSR Data RS, which is, in my opinion, quite good. There's another library that Dave McMahon wrote, who's here and going to talk after me, called HashPipe, which certainly looks a lot better. And at the surface level, it seems it's a bit more homogeneous than PSR data. You have, instead of having these disparate programs, which then just have to trust that there exists these buffers somewhere in shared memory, it's Dave can correct me if I get this completely wrong, but as far from my understanding of it, you have this one program that kind of manages the whole thing, and you have these shared objects that are your tasks, and that's is a bit more higher level in how it's orchestrated, which seems nice. And then lastly, the one I've seen that some people use is Bifrost, which might be the closest to what if we were to start thinking about what this would look like in Julia, in that it has a Python kind of top to it and a C++ backend where they have these library of blocks of operations that the user can use. And I think they're not expecting the astronomers to write their own blocks because it's in C++, just kind of put them together. But the people have been successful with this model, and it comes with a lot of nice tools, like there's something which looks like top in how you can, in the utilization of each task, things like that. But it's relatively complex in how it has been implemented. They have their own ND array abstraction, and if you want to add your own functionality like one might want to do, you have to write external code to escape the interpreter lock in Python. To give you a look at what Bifrost looks like, this is pretty much an entire pipeline definition. In Bifrost, an FRB pipeline where you read from these SIGPROC filter bank files, copy it to GPU memory, do the transpose, do an FDMT, which is a dedispersion step, copy it back to the host, and write back to a file. Pretty simple. And this will run with ring buffers in shared memory, just like PSR data does, so you can kind of smooth out the timing for moving data around and things like that. So if we were to think about doing something like this in Julia, the first, and I'm not even trying to argue that we should, but if we wanted to, because Bifrost is quite nice and people do use it, and we could do something similar, it kind of would make sense to use channels to move data between the tasks, because that's kind of the modern approach to how we share data between threads. And we can show that it can be just as fast as shared memory when used properly, and it's nice for the actual user, especially if they're used to working in C, they wouldn't have to do any explicit synchronization or mutex locks or unlocks, things like that. And something that I think is pretty important is, if you're using channels, you're getting this safe by construction setup, so you don't have to think about race conditions and things like this. And what I propose is that we could use Julia's metaprogramming facilities to come up with a domain-specific language for pipeline construction. So something like this. This doesn't exist. This is kind of what it may look like if one were to write that code, where the same as the Bifrost example, where you're reading from a filter bank file, moving it to GPU memory, doing a dedispersion step, and then coming back to writing a SIGPROC file. And I'm kind of modeling this off of the chain.jl syntax, where you're listing these chunks of operation, but instead of function composition between them, you have the same kind of ring buffer-like thing to connect the data together. And you could even, because you obviously want some parts of it that don't have ring buffers so you can save on memory, you could have a block like I have with the named block GPU here, that you only have these two channels going into this GPU block and out of it. So I think that's kind of a nice little approach, and the questions later I want to hear your feedback on this. But what does that block do? Like I said, it's going to create some kind of meta pipeline object that manages the lifetime of all of these things, creates the channels that connect them, and creates the tasks, can spawn the task based on the life cycle of the pipeline object, and will, of course, decorate some syntax for how big those channels are, things like that, whether or not you want it to be blocking or non-blocking, these kinds of details. So why would we do this? Well, compared to Bifrost, at least, it's a single language solution, which is nice because that means that if you are an astronomer and you don't know how to write or don't want to write C++, which is a very reasonable thing to do, you could write your own little custom processing thing and have it be just as fast, as the C++ block. The other thing is you get this pretty seamless GPU support with Julia. If you've used CUDA.jl before, I gave a talk last year at JuliaCon where I wrote a dedispersion kernel for fast radio bursts, and in my 20-line Julia solution, I'm just as performant as the quite large CUDA implementation that's used in a popular FRB pipeline. And I'm not particularly good at GPU programming, and if I can do that, then I'm sure the rest of the astronomers could write some absolutely incredible code. And kind of the last important bit is this could be accomplished pretty simply, I think. Bifrost leverages a lot of custom C++ in the background. Like I said, their own bespoke ND array implementation. They implemented their own JIT for some reason. And they have to maintain this library of custom blocks that they're expecting astronomers to use. So it's good for its purpose, but Julia would probably be much more flexible if this existed. And the ecosystem itself would be very, very helpful. We had this talk earlier today about thread pinning, and it looks so. One of the details in this, if you're working on like capturing data from a 100 gigabit network card, the task that does that needs to be pinned to the same NUMA node as the network card. And we have this wonderful library in Julia now, thread pinning, which would make that very, very simple. And if we're operating on a big cluster, we have distributed.jl and Dagger, which are also talks at the previous mini symposium. If we want to be really careful with reusing memory and not hitting the garbage collector as often as we could, Dave wrote a wonderful library called pool queues that we could kind of move stuff between the tasks with this queue abstraction, which is really quite nice. And of course, all of the GPU stuff as well. Why wouldn't we want to do this in Julia, though? Well, besides the fact that alternatives already exist, I'm a little worried about the timing kind of part of this and GC pauses. There was a talk from, I forgot which JuliaCon it was at, where they were doing real-time adaptive optics controls for an optical telescope, and had to mess a lot with the garbage collector to get it to really work in real time. I'm not sure how difficult that would be in a system like this. And related to that is the whole concept of packet capture. Both Dave's hashpipe library and Bifrost and PSR data provide some packet capture, because most radio telescopes, you're ingesting data as UDP packets at the very, very input if you're not reading from like a file. How do we implement high-speed packet capture in Julia? Would you even want to? We're talking about like using DPDK or some, InfiniBand, something like that, which you might want to write that in C. Not sure, but who wants to write C? And kind of the last big thing from my list here is I'm not sure if Julia's channels are fast enough. I've written a similar pipeline kind of thing using channels in Rust for GREX, and it took the people who wrote Crossbeam, which is a channels crate in Rust, quite a long time to get it to be performant. And I haven't seen that kind of level of optimization done on Julia's channels, so that would probably need some investigation. But when they do optimize it, I easily got like 60 gigabits through channels on relatively simple hardware. And last little details, if you're building like a large scale radio telescope that's running on a cluster, I'd be a bit worried about how you deploy it. Would you build would you use package compiler to like make the artifact that you actually deploy? Is that the right way to do it? How do you check for correctness in that thing that you deploy? Because we're kind of limited in static analysis tools a little bit. Although I saw some talks about JET, and I'll probably look more into that in the future. But yeah, that's my ideas. And I'm looking forward to your feedback on this before I spend any time actually trying to develop this into something real. Thank you.
All right, thanks, Kieran, for that great talk. Do we have any quick questions before the next speaker? Okay, so do you think that Julia is the right thing for this, or do you think we should be looking at something like Rust?
I think for simple things, it probably would be, because I see people write simple pipelines in Bifrost, for example, for like FRB FRB stuff, and it would be nice to have that in Julia, especially because if you're working on some, say, novel de-dispersion algorithm, I'm gonna write that in Julia, like of course I am, and then having to try to shoehorn that into some pre-existing framework would be not so nice compared to having it all be in Julia. But is it right for, like, say, the DSA 2000? Maybe, and we could talk offline if anyone has more thoughts on that kind of thing.
And
that's true.
And there's also a discussion that we'll be having from 6:10 to 7 tonight, or an open discussion where we can discuss these things as well.
For sure.
All right, let's thank Kieran again. All right. So while Dave's setting up, we'll introduce him. Dave McMahon is our last speaker. If you're in radio astronomy and I think heavy pipeline development, you've probably heard of Dave McMahon. He's developed a lot of key radio astronomy and beyond software packages, and today he's going to talk about some of his work trying to get this to work with Julia.
Almost there. There we go.
And he's going to tell us all about how we can find aliens, which is very good subject right now.
Hi, everybody. My name's Dave McMahon. I'm from UC Berkeley. I'm currently working as the chief engineer for the Breakthrough Listen project, which I'll talk a little bit about on this talk. We operate out of this thing called the Berkeley Study Research Center at UC Berkeley. I'm officially in the organizational research unit called the Radio Astronomy Lab at UC Berkeley, if you know anything about that. So I'm going to talk about how I use Julia in radio astronomy / interferometry, and the spoiler alert is I use it to find aliens, which I haven't found yet, but that's what we're doing. So I'm going to give a little bit of history of radio astronomy. I'm not sure what the people's background is here, but I figured it would be kind of maybe broader people who aren't so working day in, day out of radio astronomy, where it came from, and the history. Actually, I learned a lot preparing for this part of the talk. It's my favorite part of the talk, because it's kind of interesting. I'll introduce Breakthrough Listen. Like I mentioned, that's the project I'm currently working on. I got a few slides, a little bit of a menagerie of some radio telescopes and things, just little, like, eye candy stuff. And then I'll talk about Julia and how I use Julia. So the history, it's actually prehistory of radio telescopes, radio astronomy, because, I said in the abstract, optical astronomy has kind of been around since people could look up at the night sky. And I guess you could argue maybe it didn't really start until Galileo made his telescope and looked at the moon and Jupiter and drew the moons of Jupiter and got in a lot of trouble with the church because of that. So that still was like the 1400s, I think. So Maxwell's equations, like the mid-1860s, 1870s, something like that, predicted electromagnetic radiation, which is what we call, if the right wavelength, we call them radio waves. And so it didn't take scientists, physicists too long to hypothesize that maybe you could detect radio waves from space. And so people started to do that. But they kind of failed because of various different reasons. A lot of them was they didn't really know about the ionosphere until 1902, and they were observing at some low frequencies then, and as you may know from ham radio skipping or whatever, low-frequency radio waves do not pass through the ionosphere. They bounce either back at us or they bounce back into space, and so those were not so great. There was one guy who stretched out a very long wire on top of the mountain in the Alps, and he was trying to detect bursts of radio frequency energy from the sun. He might have been successfully at the sensitivity, and the frequency was okay, so it might have been okay, except these bursts happen during solar maximum most often, and he was observing during solar minimum. So he kind of bad luck on that one. There's one other sort of non-starter for the radio astronomy, I guess. These guys, this is 1924, Mars and Earth were passing very close to each other, and so they called up their politician, I guess, or I don't know who they called up, but they got in touch with the Navy or the Pentagon or whatever, whoever sent this telegram, and they requested the Pentagon, they convinced the Pentagon that they wanted to listen for Martians that might be transmitting to us during this close passage, and so they had the Navy turn off all the radio transmitters during the time of closest passage so that they could listen for Martians. But apparently the Martians were doing the same thing too, because they didn't hear them. So they also failed, unfortunately. It wasn't really until 1932 when Carl Jansky detected radio emission from space. But of course he did it by accident, because if he tried, he would have failed. So he did it by accident. He was actually working for AT&T Bell Labs in New Jersey, I believe, at the time, and they were building a transatlantic radio telephone, and they had some sort of hiss in their signal, and they wanted to figure out what that was. And so he built this antenna that kind of spins around little wheels. I don't know if you can see the little wheels on a little round turntable. They have a reconstruction of this antenna at the Green Bank Radio Observatory in Green Bank, West Virginia. He found two sources were related to storms. The third source he found was something that just sort of happened, and it happened every day. And he thought, well, that's kind of weird. And then he noticed that it wasn't like every 24 hours, it was every 23 hours, 56 minutes, which implies that it's something on the star, well, like in the cosmos, in the sidereal day, they call it. It's fixed against the stars. It's not, it's part of the sun-Earth cycle. So it turns out it was the, well, probably maybe Sagittarius star, actually. It was the galactic center. So, yeah, before you imaged it, he detected it, I guess. So, 1932, that was the first thing from space, radio emission from space that we detected. I was talking to someone at one of the evening events this week, and my understanding was, or maybe it was Monday, anyways, my understanding was that he was transferred to a different project and didn't really pursue this. But I'm not sure what the full story is, but he didn't really take it anywhere. And this guy who was, I guess, a college student around that time, graduated. His name was Grote Reber. He actually built the first parabolic dish reflector to capture radio waves from space. And he was the first and only radio astronomer in the world for about 10 years. And even with this telescope and everything, it took him a couple of years to get it to work and actually get data in. But he did succeed. He was quite successful. He wanted to publish his results, and he had some challenges finding a peer-reviewed journal that would actually take it, because the astronomers didn't understand the radio part of it, and the radio engineers didn't understand the astronomy part. And so he went back and forth with the editor, and eventually they published his paper unreviewed, which is kind of amazing. But it was legit work, and people did quickly, follow up with other work in a similar vein. After World War II ended, all these radar engineers sort of had, to find new jobs, I guess, and some of them went to radio astronomy. So that was pretty good. And from there, the field took off to where it is today. In 1960, Frank Drake started Project Ozma. This is sort of perhaps one of the first radio SETI experiments. Frank Drake, maybe you know of the Drake equation. It's sort of a formula that's just designed to sort of estimate how many civilizations there may be, communicating civilizations there may be in our galaxy. And it has a bunch of terms in it. I won't go through that today, but it's a fun thing to talk about. This is sort of his setup here in the upper left corner there. It's kind of fun to go to see these old things, and they have the big knobs and the fancy lamps and the switches and everything. But this was their back-end system they had back then. It's a chart recorder. Yeah, it's not a lot of resolution. This was, I guess he was observing on Christmas Day. This is 25 December. This is a modern back-end. Looks kind of like a cluster. This is the Briggs-Wilson cluster. We have at Green Bank now. It's about 72 compute nodes, a few more actually than since these pictures were taken. Mostly a lot of disks and GPUs and network cards, which I guess is what computers are these days, or clusters. This was the early archive, how we archived his data. With chart recorders, you just put them in a cardboard box and you put them in a cabinet, and then there it is. It's not really indexed or anything like that. So yeah, good luck finding something. This is what a modern archive looks like. It's like the same thing. So Breakthrough Listen is the project I am currently engaged with. It was announced back July 20th, 2016 at the Royal Society in London, and it's from the Breakthrough Initiatives. It's the first of the Breakthrough Initiatives. The Breakthrough Prize Foundation started these initiatives. They do the Breakthrough Prize Awards every year. In fact, your group got a Breakthrough Prize Award. There's a funny story I can tell you after hours about that whole situation. It's a 10-year project, $100 million. It's a pretty good chunk of change. These are the people that were there at the announcement. Urian Milner's the prime sponsor, Stephen Hawking, Lord Martin Rees, Frank Drake, and Anne Druyan, Carl Sagan's widow. And they had some big statement and signatory, a lot of pomp and circumstance with the announcement. Yeah, so that's sort of what I do. It's initially we started with 3 different telescope facilities. The automated planet finder, it's an optical component, so I don't do much with that. But that's in California, very near to Berkeley. It's just down in San Jose, up on Mount Hamilton, sorry. Lick Observatory is there. The Green Bank Telescope in Green Bank, West Virginia, that's part of the eye candy coming up, just so you know. It's very large, and it's quite an amazing facility that this thing is so huge and they can still point it so precisely on the sky. It just blows my mind every time I think about that. And we were also on the Parkes Radio Telescope. It's now called the Murray-Yang Telescope at the Parkes Observatory. It's in New South Wales, Australia. This was famous for, well, the movie called The Dish, but also it was one of the downlinks for the Apollo moon mission. So I think, I'm not sure if it was the actual stepping onto the moon that was video, but it was a lot of the video of that whole thing. It's if you've seen the movie The Dish, it's actually a really good movie. If you haven't seen it, I would suggest you see it. It's quite a charming little film. Now these are all the facilities we're at now. We have about, I guess this says 16, or it said 16 before I expanded the list. We're basically almost on every continent. I think we don't have anything on Antarctica yet, but we sort of have a global domination. I guess we're kind of in competition with you, but we get lower frequency, so it's easier for us to engage with people. And we also operate a lot of times in a commensal setting where we will just take a copy of the data that some other observer is observing some other source, because we don't really know where ET might live, so any place it's good to look as another place. We tend to look at stars when we do our thing, because stars have planets, and presumably people live on planets. There could be a Battlestar Galactica kind of concept, but so here's the menagerie part of the talk. This is the Green Bank Telescope. It's kind of like the Golden Gate Bridge or any big bridge. They have to paint it regularly, and so these are the painters here lined up with their hard hats on over there, and they have this sort of forklift kind of thing here. And this is the Green Bank Telescope, and those are where the people are down there. And you can see the pickup truck sort of for scale. I mean, it's 100 meters, diameter. The aperture is 100 meters. I think the surface is probably about 110 because it's kind of at an angle. Yeah, it's just a really, really cool place to visit. This is not a radio telescope. This is the Leviathan telescope. This is an old optical telescope. It's in Ireland. It's at the Burr. It's in Burr at the Burr Castle. There's a LOFAR station there, and we do actually work. We have some back-end equipment at that LOFAR station and at the Sweden LOFAR station for low-frequency observations, and we do some simultaneous observations, which is kind of a fun way to cut down on RFI false positives. But this telescope is very famous because the guy who built this was the Earl or something of this county or whatever region it was. And he would go up every night and look at this thing, and he would have a drawing of this, M51, Messier, his catalog, and this is the 51st object. And he would just keep updating his drawing, talk about your averaging of your images. And a form of integration, a sort of artistic integration, he would just every day kind of tweak his drawing to see whatever parts he could see the best. And he was the first person to resolve the structure of galaxies. Before they were just fuzzy blobs. And he tried to get some of his, colleagues or other astronomers in the UK interested in this, and they're like, no, some instrumental flaw. Don't bother us with this silliness. Eventually he convinced them to come out and look for themselves, and they did, and they're like, oh, wow, it is real, okay. So it's now known as the Whirlpool Galaxy, which they didn't call it that until they resolved the structure and everything. So, yeah, it's a fun story, and more history. But then again, that was, I think, in the mid-1850s. I think that predated even Maxwell's equations, possibly. It's right around the same time. We also work on telescope arrays. So on the left is the Meerkat radio telescope array that's in South Africa. It's a very powerful telescope. They've made some fantastic maps of the galactic center, much larger scale than yours. But they've made some really cool maps with some really bizarre filaments and such. How are we doing at time, Paul?
You got 4 minutes.
4 minutes, all right. The bottom one is a very large array in New Mexico. We have a big back end on that, which I was going to put out, but I just had to stop at some point with the eye candy. Let's get on to the Julia stuff. This is also Edelman telescope array at the top. We take a lot of students up there and everything like that. It's kind of a teaching array, and it's operated by the SETI Institute, actually. But we work with them up there at that facility. That's in Northern California. Okay, Julia. How to find ET. This is a test signal sort of that we use. It's not really a test signal, it's just a signal from the Voyager 1 space probe. And we use it as sort of what a putative ET signal might look like. It's drifting in frequency, so the horizontal axis is frequency, the vertical axis is time. We call this a waterfall plot. It's shifting in frequency. This is very finely channelized. This is the carrier from the Voyager 1 signal. There's some sidebands that are a couple 22 kilohertz out either direction, and this is drifting because the Earth is spinning. It's primarily due to Earth's rotation, and so as the Earth spins, it's an acceleration. So, the Doppler shift is because there's motion between the transmitter receiver. It's like an audio thing with the train. Gets quiet, higher and higher in frequency, and then whistle goes down. So the shift is because of the velocity, but the drift or the change in the shift is because of the acceleration. Rotation is an acceleration kind of thing. And so what we want to do is we want to find this signal, and we want to add it all up. And so what you want to do is you want to kind of stack them. You want to kind of undrift the signal. And you can do it two ways. You can do it through just doing a discrete shift by integer number of channels, just sort of sliding them over. You don't have to actually slide them, you just like move, index differently, but it sort of effectively does this sort of thing. Or you can also do a Fourier domain shift where you take the FFT of the spectrum, multiply by a complex sinusoid, inverse FFT it back, and then the signal's been shifted. There's a little bit of wraparound at the ends, but we usually do really wide bandwidths and not that much shifting. So we just ignore the little edge effects. And then you can integrate down over time, and so when they're all lined up, you get this sort of big spike, and when they're not lined up, you get the red curve. It's just sort of not so bright. And this is a pretty bright signal, actually, from the Green Bank telescope, and it's been super channelized. So it's right. This is for us. That's the high SNR kind of signal, even though it's actually quite low. But radio astronomy is just all about low SNR. It's like mostly just noise. So we need to integrate to get the noise down and the power up. So you can do this one by one. If you do this, like this is one drift rate we chose. It happened to be 2.37, which was the magic one to do. If you do it at different drift rates, and this becomes like, if you could imagine this, instead of being a curve, you could imagine a color, like a row, raster row in a heat map. And so if you do that for all these different drift rates and different starting frequencies, you get this thing, which we kind of call a butterfly plot or something. It's a frequency drift rate plot. And you can see all the power is at this drift rate, and the drift rate and the bright spots. It tells you the start channel and the drift rate. And it turns out that you can use the chirp Z transform to kind of do this like all at once for a whole bunch of drift rates. So you FFT the spectrum, you do a chirp Z transform. This is sort of you start up on the upper left. You do that's your time frequency sort of waterfall plot spectrogram. You do an FFT of that into the Fourier domain, and then you do a chirp Z transform, and then you do another inverse FFT back, and then you end up with your FDR plot, and it's pretty cool and fast and interesting. I wrote an implementation in Julia. It was super easy to, I just wrote it using arrays in FFTW, but then it was super easy to switch to CU arrays and CUDA FFT, and I profiled it and was able to get it all, parallelized, so everything happens in parallel. And the limitation factor here, it's I/O bound. It's actually O bound. This is the memcopy device to host of the output data, and it's just sending data out as fast as it can. And so it's not compute bound, and so we can do more of the compute on the GPU perhaps. So there's some room for moving the compute. Also visualizing data. This is one other thing I use Julia for. This is some green bank data. This Iridium satellite stuff is really a problem for us. They've had more launches since our program launched. They've had more and more space vehicles going around, and so I think it's become more of an issue for us. And you can see it really corrupts our data because it causes overflows in the FFT for that sort of portion there. And so then if you look at the bottom left plot, that's a big long, well, it's only an hour, I guess, and each little gray line is a scan that we do, but you can see the total power of the satellite kind of comes and goes. It's not so good. And so then I use Satellite Toolbox, and you get all the two-line elements for the Iridium satellites. You can make a little sky map of where the satellites were for the 5 minutes of this scan, and it's sort of like, the little circle, black circle is where the telescope was pointing. The traces show where the satellites were going, and one of them came pretty close. So yeah, that's another thing. And it's just super convenient to do all this stuff. This was like, you see the packages that I used there. Voyager localization, we're also trying to do some beamforming on the Voyager test signal. We can't get the location from JPL horizons. They tell us where they think it is. It's pretty close, like it's close enough for the GBT to see it and find it. But when you're doing the VLA beamforming on it, the beam is much, much smaller, the synthesized beam size. And so you beamform where JPL says it is, and it's not there. And so we wanted to find out where it actually was. So we did some sort of little raster scans sideways and vertically, like in right ascension and declination, on the Voyager's location. And then you take the total power, and you can do like fit a Gaussian to the beam shape and that sort of thing, and find out where it is. And this is talking about some of the hash pipe data buffer stuff that Kieran talked about. And these are the repos that I have for some of the stuff I've written. You can look me up. I have my own little registry there if you want to just add that and use my stuff. That's an easy way to do it, because I haven't really registered any of these in the general registry yet. So that's it. Thank you.
All right. I think we have time for like one quick question, and then I want to let you go to the Wolfram keynote. So, any quick questions?
None? Aliens, come on.
I mean, I do, but I also want to do it.
Okay.
Again, there'll be a discussion later, and
come ask me anytime. Yeah, I'm happy to talk about it anytime.
All right. Thank you, everyone. Thank Dave again.
Thanks.
Figure out how to kill them with some one. I can send. Okay.
one guy